There is something happening right now that is so familiar it rarely gets questioned. You are aware, not just awake, not just reacting, but experiencing. Sounds arrive, thoughts drift in and out, sensations quietly announce that you are here, and all of this feels effortless, as if it could never have been any other way. Yet the strange part is this. Science can measure almost everything around that experience: electrical signals, chemical exchanges, networks switching on and off. It can even predict in some cases what you're about to notice before you notice it. But the experience itself never shows up as a neat object. It does not sit in one place in the brain. It does not glow on a scan. It does not come with a label that says this is consciousness. Instead, it has to be inferred, carefully, indirectly, through patterns, absences, changes and moments where awareness fades, fractures, or unexpectedly returns. Tonight is about that quiet investigation, not about big claims or mystical answers, but about how scientists actually study consciousness, what they have learned so far, and where the honest limits still remain. The goal is not to make the mystery louder, but to make it clearer. Welcome to The Sleepy Scientist. If you enjoy calm, thoughtful explorations of how reality works, please like and subscribe. And while awareness is quietly doing its thing right now, where are you watching or listening from? Consciousness is the most familiar fact of life, and also the easiest one to misunderstand. Right now, something is happening. A sound arrives, a sensation flickers, a thought forms and dissolves. Even if nothing in particular stands out, there is still a quiet sense of being here, a point of view, a field in which anything at all can appear. That simple presence is what is meant by consciousness, not intelligence, not cleverness, not skill or memory or language, just experience itself. This distinction matters because the word consciousness is often used as a kind of intellectual suitcase, packed with every impressive mental ability humans happen to value. Intelligence gets placed inside it, memory follows, language, emotion, self-control, planning, creativity, reasoning. Eventually the suitcase will not close, and the discussion collapses under its own weight. So the first task is restraint. Consciousness is subjective experience, the felt side of reality, the difference between information existing somewhere in the world and that information being lived from the inside. A calculator can solve problems without experiencing anything. A computer can recognize faces without knowing what a face feels like. Performance alone does not guarantee awareness. Consciousness is not what a system can do. It is what it is like to be that system, if anything at all. Memory, for example, is not consciousness. Memory allows information to be stored and retrieved across time. Consciousness exists only in the present moment. An experience can happen and later be forgotten. Information can be stored without ever being vividly experienced. Memory and consciousness interact constantly, but they're not the same thing. Language is another frequent source of confusion. Language allows experience to be described, shared, categorized, and shaped. But experience does not require words. Infants have experiences long before language develops. Many animals almost certainly have some form of experience as well. Even adult humans regularly encounter experiences that resist clear description, yet feel completely real. Emotion also does not define consciousness. Emotions color experience, sometimes dramatically, sometimes subtly, but they are contents within consciousness, not consciousness itself. A calm mind is still conscious. A numb mind is still conscious. Even a mind that feels strangely empty can retain a faint sense of being present. Attention, too, is often mistaken for awareness. Attention is the brain's way of selecting and prioritizing information. It determines what gets processed deeply and what fades into the background. Attention can sharpen experience, but it is not identical to it. The sound of a refrigerator can be part of experience without being attended to. A sudden movement can capture attention before there is a clear sense of what was seen. Attention and consciousness overlap, but they can separate. Executive control is another nearby concept that needs to be set aside. Executive control refers to deliberate guidance of behavior, holding goals in mind, suppressing impulses, and choosing between actions. Consciousness can persist even when control is weak. Dreams are a clear example. Experience can be vivid, emotional, and immersive, while logic and self-control loosen their grip. Awareness does not require tight management. These separations are not philosophical hair-splitting, they are practical necessities. Without them, it becomes impossible to design experiments that actually target consciousness, rather than some neighbouring process. Once consciousness is defined narrowly as subjective experience, another crucial distinction becomes visible: the difference between being awake, being responsive, and being consciously aware. Wakefulness is a biological state. It reflects activity and arousal systems that keep the brain capable of sustained interaction with the environment. Responsiveness is behavioral. It refers to observable actions such as speaking, moving, or following instructions. Conscious awareness is the inner aspect, the felt presence, which can vary independently of both. Everyday life provides an easy illustration. A person drives a familiar route and later realizes that parts of the journey barely registered. The eyes were open, the hands responded appropriately, the behavior looked competent. Yet awareness was thin, drifting, and only loosely connected to what the body was doing. The brain ran an automated routine while consciousness wandered elsewhere. This is not a malfunction. It is a feature of a system designed to conserve effort. Behavior can remain smooth while awareness narrows. That fact alone makes it clear why outward performance cannot be taken as a reliable indicator of inner experience. The opposite dissociation also occurs. During certain stages of sleep, responsiveness drops dramatically, yet experience can continue in the form of dreams. The body lies still, disconnected from voluntary movement, while the mind constructs entire worlds. Awareness persists even when responsiveness disappears. These examples show that consciousness is not an on-off switch tied directly to wakefulness or action. It is graded, flexible, and capable of existing in altered forms. This brings the discussion to a well-known framework introduced by David Chalmers. He distinguished between what he called the easy problems and the hard problem of consciousness. The phrase easy problems is misleading if taken literally. These problems are not easy in the everyday sense. They include some of the most demanding work in neuroscience and psychology. They're called easy only in a technical sense, meaning they concern functions and mechanisms that science is well equipped to investigate. How does the brain discriminate stimuli? How does it integrate information from different senses? How does it direct attention? How does it store and retrieve memories? How does it generate speech and guide behavior? These questions are extremely difficult, but they are approachable through experiments, models, and measurement. The hard problem points at something different. Not what the brain does, but why any of it is accompanied by experience at all. Why information processing is not dark and silent. Why there is something it feels like to see, hear, or think. Researchers disagree about how to interpret this distinction. Some argue that the hard problem will dissolve as neuroscience advances. Others believe it highlights a conceptual gap that may remain even with complete data. What matters here is not choosing a side, but recognizing that this tension shapes how theories of consciousness are framed. To keep discussions precise, scientists often introduce another useful distinction. Phenomenal consciousness refers to the felt quality of experience itself. The sharpness of pain, the warmth of sunlight, the color of a surface, the texture of a sound. It is the what it feels like aspect. Access consciousness refers to information that is available for reasoning, report, and deliberate action. If a perception can be held in mind, described, compared, and used to guide behavior, it has access. These usually travel together, but not always. Dreams can have strong phenomenal character while access is unstable. Some information can influence behavior with surprisingly weak reported experience. Different theories interpret these cases differently, but the distinction helps prevent vague language from doing too much work. At this point, a fundamental constraint becomes unavoidable. Consciousness is private. It is first person. Science depends on public evidence. It works with observations that can be shared, measured, and repeated. Experience is known directly only to the one having it. Evidence is always third person. This does not make consciousness unscientific, but it defines the challenge. Consciousness cannot be observed directly in the way a cell or a planet can. Instead, it must be inferred from patterns, comparisons, and changes across conditions. This is where the idea of neural correlates of consciousness comes in, commonly abbreviated as NCC. An NCC is defined carefully as a neural pattern that reliably accompanies a particular conscious experience. When the experience is present, the pattern appears. When the experience is absent, the pattern disappears. The definition is intentionally modest. It does not claim the pattern is the ultimate cause of experience. It does not claim it explains everything. It simply identifies a relationship that can be measured, tested, and refined. This modesty is deliberate. By focusing on correlates rather than final explanations, science gains a foothold without pretending to have climbed the entire mountain. Of course, correlates can mislead. A brain signal might reflect attention rather than experience itself. It might reflect the act of reporting rather than the experience being reported. This is why no single signal is ever treated as decisive. To manage this complexity, consciousness research relies on operational definitions. An operational definition specifies how a concept will be measured in a particular experiment. It does not claim to capture the full nature of consciousness. It states what will count as evidence for awareness in that context. One study might define awareness as accurate verbal report. Another might use confidence ratings. Another might rely on specific brain patterns identified in earlier work. Each choice captures something real while leaving other aspects aside. The strength of the approach lies in convergence. When different operational definitions point in the same direction, confidence increases. When they diverge, the disagreement becomes informative rather than embarrassing. So the foundation is set. Consciousness refers to subjective experience, not performance or intelligence. Wakefulness, responsiveness, and awareness are related but distinct. Phenomenal character concerns felt quality, while access concerns availability for reasoning and control. The NCC provides a measurable foothold rather than a final answer. Operational definitions allow public evidence to constrain private experience without pretending to exhaust it. With these tools in place, the study of consciousness becomes possible, not simple, not complete, but careful, grounded, and honest about what can be known and how it is known. Studying consciousness immediately forces science into an unusual position. Experience happens privately. Evidence does not. A sound is heard by someone. A colour appears to someone. A thought feels like it belongs to someone. But none of that is directly visible from the outside. There is no instrument that can look inside a mind and watch awareness unfold in real time. Science has to work with what leaks out into the world instead. What a person says, what a body does, what a brain produces that instruments can detect. So the central task becomes translation. How does a private experience leave a public trace? The most natural place to start is verbal report. A participant is shown something and asked what they experienced. Did you see the image? Did you hear the tone? Did you feel the stimulus? In everyday life, this is how experiences are shared, so it feels intuitive to treat report as a direct window into awareness. And report really is useful. It allows subtle distinctions. A person can describe clarity versus vagueness, confidence versus uncertainty, surprise versus expectation. These details matter, and without report many aspects of experience would remain inaccessible. But report is never a pure readout of experience itself. To report an experience, the brain must do far more than experience it. Attention must be directed to the stimulus. Information must be held briefly in working memory. A decision must be made about what to say. Language systems must assemble a response. Motor systems must execute it. Motivation must be present to engage with the task at all. All of that additional machinery produces brain activity of its own. So when brain signals are recorded during report, some of what appears reflects experience, and some reflects everything required to describe that experience. Separating the two is one of the hardest problems in the field. This is why researchers rarely rely on report alone. Instead, they supplement it with other behavioral measures designed to probe awareness from different angles. Confidence ratings are one example. Rather than asking only what was perceived, participants are also asked how confident they are in their response. Confidence can track aspects of awareness that accuracy alone misses. Two answers can be equally correct, yet feel very different from the inside. Reaction times provide another layer. Faster responses often indicate clearer or more accessible information, while slower responses can reflect uncertainty or weak signals. Reaction time does not tell us what an experience felt like, but patterns across many trials can reveal important structure. Forced choice tasks take this further. Instead of allowing a participant to say they saw nothing, the task requires a choice between alternatives, even if the participant feels unsure. This can reveal sensitivity to information that never becomes a confident experience. At the same time, it highlights an uncomfortable fact. Behavior can be guided by information that does not always feel consciously present. This is one of the key reasons behavior cannot be treated as a direct proxy for experience. The brain can process information, guide actions, and improve performance without awareness necessarily following along. Because report and behavior are so tightly entangled with additional processes, researchers began searching for ways to infer experience without asking people to describe it at all. This led to what are known as no-report paradigms. The idea behind no-report paradigms is simple. If reporting adds extra brain activity unrelated to experience, then removing report should leave a cleaner signal. Instead of asking participants what they experienced, researchers design experiments where experience changes while behavior remains constant, or where indirect physiological signals reveal what is likely being perceived. Eye movements, pupil size, spontaneous reactions, and predictable reflexes can sometimes indicate which stimulus is being experienced without any explicit report. In other cases, experimental designs allow two conditions to differ in experience while keeping task demands identical. No report paradigms are not a perfect solution. They still rely on assumptions and inference, but they serve an important purpose. They remind researchers that report is a tool, not a definition of consciousness itself. Behavioral measures, however refined, still leave a gap. To narrow that gap, consciousness science turns to the brain. One of the most widely used methods for measuring brain activity is electroencephalography, commonly abbreviated as EEG. It records electrical activity produced by large populations of neurons, measured at the scalp using electrodes. Its greatest strength is timing. It can track changes in brain activity on the scale of milliseconds, making it well suited for studying fast perceptual events. This allows researchers to ask when certain signals appear relative to a stimulus or a reported experience. Some signals emerge very early, reflecting initial sensory processing. Others appear later and may reflect attention, integration, or decision processes. The limitations of EEG are just as important. Spatial resolution is limited. Signals recorded at the scalp are blurred mixtures of activity from many underlying sources. Pinpointing precise locations is difficult, and interpretations must remain cautious. Another major tool is functional magnetic resonance imaging, commonly abbreviated as fMRI. fMRI does not measure neural activity directly. Instead, it measures changes in blood flow and oxygenation that tend to accompany neural activity. Its strength lies in spatial detail. fMR can localize activity to specific brain regions far more precisely than EEG. This makes fMRI valuable for mapping networks involved when experience changes. It has been instrumental in identifying large-scale patterns associated with perception, attention, and awareness. Its limitation is speed. Blood flow changes unfold over seconds, not milliseconds. fMR cannot capture the rapid dynamics of experience as it happens. What it shows is a delayed echo rather than the activity itself. A complementary technique is magnetoencephalography, commonly abbreviated as MEG. MEG measures the magnetic fields produced by neural electrical activity. Like EEG, it offers excellent temporal resolution. Compared to EEG, it can sometimes provide improved spatial localization, because magnetic fields are less distorted by the skull and scalp. However, MEG systems are expensive and technically demanding, and they are primarily sensitive to activity in certain cortical regions. Like all methods, MEG offers a partial view rather than a complete picture. Recording techniques reveal correlations between brain activity and experience, but correlation alone is not enough. A brain pattern can reliably accompany awareness without being necessary for it. To move closer to causation, researchers use perturbation. One of the most common non-invasive perturbation tools is transcranial magnetic stimulation, commonly abbreviated as TMS. TMS uses rapidly changing magnetic fields to induce brief electrical currents in targeted regions of cortex. This can temporarily disrupt or modify neural activity. By observing how experience or behavior changes when a region is perturbed, researchers can test whether that region plays a causal role. If disrupting a region reliably alters experience, that suggests necessity. If disrupting it has no effect on experience despite strong correlations in imaging data, that correlation may be incidental. TMS has limits. Its effects are relatively superficial. It cannot directly reach deep brain structures. Its influence is temporary and context-dependent. But when combined with recording methods, it becomes a powerful way to probe function. None of these methods stands alone. Each has strengths, each has weaknesses, each captures a different aspect of the relationship between brain and experience. This is why consciousness science relies so heavily on converging evidence. A finding becomes more compelling when multiple lines of evidence point in the same direction. When behavior changes systematically, EEG shows corresponding timing differences, fMRI highlights relevant networks, and perturbation alters experience in predictable ways, confidence increases. Converging evidence also protects against overinterpretation. If a result appears only in one method and disappears in others, caution is warranted. The goal is not dramatic claims, but patterns that survive different approaches. Throughout all of this, a crucial discipline must be maintained. The proxy must never be mistaken for the thing itself. Report is not experience, behavior is not experience, brain signals are not experience, they are indicators, constraints, and clues. By combining them carefully, science can speak meaningfully about consciousness without pretending to observe it directly. The result is not a perfect picture, but a disciplined outline, shaped by evidence and honest about its limits. That discipline is what allows the unseen to become scientifically tractable, without losing sight of what makes consciousness such a difficult and fascinating subject in the first place. If consciousness leaves traces in the brain, the obvious question is where to look for them. This question sits at the center of what neuroscientists call the search for neural correlates of consciousness, often shortened to NCC. The goal is not to explain consciousness all at once, but to identify patterns of brain activity that reliably go along with conscious experience and that disappear when experience disappears. One of the most influential pushes to make this search concrete came from Francis Crick and Christoph Koch. Their motivation was practical rather than philosophical. Instead of debating what consciousness ultimately is, they argued that researchers should focus on isolating the minimal neural activity that changes when experience changes and nothing else does. The emphasis on minimal was important. The brain does many things at once. It controls posture, regulates breathing, monitors the internal state of the body, predicts outcomes, and prepares actions, most of which never enter awareness. If everything active in an awake brain were treated as part of consciousness, the concept would quickly lose meaning. So the early challenge was to narrow the target. Initial efforts often focused on the idea of local hotspots. Certain regions of cortex, particularly in sensory areas, seemed tightly linked to experience. Damage to parts of visual cortex, for example, could remove specific aspects of vision. Lesions in somatosensory regions could alter touch or pain. These findings encouraged the thought that consciousness might live in particular places, perhaps even a single center where experience was generated. This idea had intuitive appeal. If vision feels visual, perhaps it lives in visual cortex. If sound feels auditory, perhaps it lives in auditory cortex. Find the right place, and the mystery might crack open. But the brain resisted that simplicity. As experimental methods improved, researchers found that activity in sensory regions often occurred even when stimuli were not consciously perceived. A visual signal could pass through early visual cortex without ever reaching awareness. At the same time, other regions became active during tasks that involved reporting, deciding, or responding, regardless of whether the experience itself was vivid. It became increasingly clear that no single area lit up only when consciousness was present and stayed silent otherwise. Hotspots were involved, but they were not sufficient on their own. This forced a shift in perspective. Instead of asking where consciousness is located, researchers began asking how information is processed, shared, and stabilized across the brain. The focus moved from isolated regions to interactions between regions, from static locations to dynamic patterns, from places to processes. One reason for this shift was the temporal character of experience. Conscious perception is not just about detecting a stimulus. It involves maintaining a coherent experience long enough for it to be noticed, compared, and potentially acted upon. Brief local bursts of activity might reflect unconscious processing, while conscious experience seemed to require activity that was sustained and coordinated over time. This led to growing interest in distributed networks and long-range communication. Rather than residing in one cortical island, consciousness appeared to involve patterns that linked multiple regions together in stable ways. At the same time, researchers realized that not all correlates were created equal. Some brain signals seemed to track whether a person was generally awake and responsive, while others tracked what the person was experiencing at a given moment. This distinction is often described as the difference between level and content. The level of consciousness refers to the overall presence and richness of experience. It distinguishes being awake from being deeply asleep or under general anesthesia. The content of consciousness refers to what fills that experience at any given time: a face, a sound, a memory, a pain, a colour. These two dimensions can vary independently. A person can remain fully awake while the contents of experience change rapidly. A sound appears, a thought intrudes, attention shifts, and the level remains stable. Conversely, the level can drop while some processing continues in the background. Recognizing this separation helped refine the search for NCC patterns. Content-specific correlates aim to identify brain activity linked to particular experiences rather than to general alertness. For example, if a face is consciously perceived on one trial but not on another, while task demands and wakefulness remain constant, differences in brain activity are more plausibly tied to conscious perception itself. This approach allows researchers to hold level steady while varying content, which helps isolate signals related to awareness rather than arousal. However, even content-specific contrasts are vulnerable to confounds. Attention is one of the most persistent. Attention can amplify neural responses and improve behavioral performance even when experience itself is weak. A stimulus can capture attention without being clearly experienced, and an experience can sometimes occur without focused attention. Brain activity related to attention can therefore masquerade as a marker of consciousness if experiments are not carefully controlled. Decision-making introduces another layer of complexity. Many experiments require participants to decide whether they perceived something. Neural activity associated with forming that decision often appears later in time and spreads across frontal and parietal regions. If not accounted for, this activity can be misinterpreted as a signature of awareness, rather than a signature of choice. Working memory adds further noise. Holding information in mind recruits additional systems that are not strictly required for experience itself. A brief experience that is immediately forgotten may leave a different neural trace than one that is maintained for later report, even if the initial experience felt similar. Motor planning can also intrude. Preparing to press a button or speak engages motor and premotor areas that have nothing to do with experience itself. These signals can appear reliably whenever a response is required, regardless of what was actually experienced. These confounds do not invalidate the search for NCC, but they raise the standard. A convincing correlate must survive attempts to separate experience from attention, decision, memory, and action. This is where evidence from brain damage becomes especially valuable. Lesion studies provide a way to test necessity rather than mere association. If a particular region or network is truly required for a specific aspect of conscious experience, damage to that region should disrupt that experience in a systematic way. Clinical cases have shown striking dissociations. Damage to certain visual areas can remove color experience while leaving shape perception intact. Damage to parietal regions can eliminate awareness of one side of space while preserving awareness on the other. These cases demonstrate that conscious contents can be selectively lost, rather than disappearing all at once. Lesions, however, are rarely tidy experiments. The brain can reorganize. Damage often affects multiple pathways. Interpretation requires care. To complement lesions, researchers use stimulation as a reversible form of causal testing. Electrical stimulation during neurosurgery, or non-invasive magnetic stimulation, can temporarily alter activity in targeted regions. If stimulating a region reliably changes experience, that suggests a causal contribution. If stimulation has no effect on experience despite strong correlations in imaging data, that correlation may not be essential. Stimulation evidence helps separate passengers from drivers. It asks not just where activity occurs, but what happens when that activity is disrupted. As these approaches accumulated, a more nuanced picture of neural correlates emerged. Some correlates appear early and locally, reflecting initial sensory processing. Others appear later and involve interactions between distant regions. Some track specific contents, while others track overall availability and integration. No single signal has emerged as a universal marker of consciousness. Instead, the debate has shifted toward how these pieces fit together. Is consciousness primarily local, arising within sensory regions through recurrent processing? Is it global, requiring widespread integration across the brain? Or does it involve a hybrid architecture, where local content processing becomes conscious only when embedded in stable system-level patterns? Different theoretical frameworks answer these questions in different ways, but they are constrained by the same evidence. Any viable account must explain why consciousness can change while wakefulness remains constant, why contents can shift rapidly within a stable level, and why disrupting some processes abolishes experience while disrupting others does not. This is why separating level from content has been so productive. By holding one constant while varying the other, experiments can target specific aspects of awareness. A person can remain awake while conscious contents blink in and out. A person can lose general awareness while some processing continues. Each dissociation narrows the space of possible explanations. Throughout this work, restraint has proven essential. Not every reliable brain signal is a marker of consciousness. Not every late signal reflects awareness. Not every widespread pattern implies experience. The history of the field includes many confident claims that did not survive better controls or replication. Progress has come from treating NCC as a moving target rather than a finished discovery. Patterns are proposed, tested, challenged, refined, and sometimes discarded. This slow, careful process is not a weakness. It is what rigorous inquiry looks like when the subject is intimate, complex, and easily confused with its own measurements. The search for neural correlates has reshaped the study of consciousness itself. The focus is no longer on finding a single place where experience magically appears. It is on understanding how patterns of activity relate to the presence, stability, and content of awareness, and how those patterns depend on interaction, timing, and structure rather than simple location. The mystery remains, but it now has contours. Consciousness leaves traces in the brain, but those traces are subtle. context-dependent, and intertwined with other processes. Untangling them requires patience, careful experimental design, and a willingness to accept partial answers. That discipline is what allows the science of consciousness to move forward, slowly but steadily, guided by evidence and honest about what remains unknown. One way to bring order to the growing evidence about consciousness is to ask a very practical question. What does conscious information actually do that unconscious information does not? This question sits at the heart of global workspace theory, a functional account that treats consciousness not as a thing or a place, but as a particular role information can play inside the brain. The core idea was introduced by Bernard Baars. His proposal was deliberately grounded and almost mundane. The brain, he suggested, is made up of many specialized systems working in parallel. Vision analyses shapes, color, and motion. Hearing tracks pitch and rhythm. Motor systems prepare actions. Memory systems retrieve fragments of past experience. Emotional systems evaluate significance. Most of this activity happens quietly, outside of awareness. Consciousness, in this view, is not the sum of everything the brain is doing. It is what happens when a particular piece of information becomes globally available to many of these systems at once. Baars used the metaphor of a workspace to describe this process. The metaphor is important, but it must be handled carefully. This is not a literal space inside the skull, and it is not a tiny theatre with a spotlight and an audience. It is a way of describing a functional arrangement. When information enters the workspace, it is no longer locked inside one specialized process. It becomes shareable. It can influence memory, decision-making, planning, language, and action simultaneously. Information that remains outside the workspace can still shape behavior, but only in narrow, task-specific ways. It stays local. It does not get broadcast. This idea helped explain a familiar feature of experience. Conscious contents tend to feel unified and flexible. When you are aware of something, you can think about it, talk about it, remember it later, compare it with other things, and use it to guide choices. Unconscious processing, by contrast, is often rigid and context-bound. It does its job and stops. Over time, this broad framework was developed into a more explicit neural model known as the global neuronal workspace, most closely associated with Stanislas Dehaene and Jean-Pierre Changeux. The global neuronal workspace model keeps the same functional idea, but anchors it more firmly in brain architecture. It proposes that conscious access depends on the rapid, coordinated activation of a distributed network of neurons, particularly involving frontal and parietal regions that are well positioned to communicate with many other systems. In this model, sensory areas process incoming information first. Much of this processing remains local and unconscious, but under certain conditions the activity crosses a threshold. It becomes amplified, stabilized, and broadcast across long-range connections. At that point, the information enters the global workspace. This transition is often described using the term ignition. Ignition does not mean a literal spark or explosion. It refers to a sudden nonlinear change in brain activity. A weak, fleeting signal becomes strong and sustained. Activity that was confined to sensory regions suddenly involves distant areas. The representation becomes robust enough to be held in mind, reported, and used flexibly. One of the key claims of the global neuronal workspace model is that conscious perception is all or nothing at the level of access. A stimulus is either globally available or it is not. There may be graded processing before that point, but once ignition occurs, the information becomes widely shared. This claim makes the theory attractive because it generates testable predictions. If consciousness depends on global availability, then conscious content should show certain properties. They should be more stable over time, they should be easier to remember, they should be accessible to many different tasks. They should influence reasoning, planning, and voluntary action in ways that unconscious information cannot. Researchers have tested these ideas using classic experimental paradigms designed to separate early sensory processing from later access. One such paradigm is visual masking. In these experiments, a stimulus is presented very briefly and then quickly followed by another stimulus that interferes with its processing. Even though the first stimulus reaches early visual areas, participants often report no awareness of it. Brain recordings show early sensory responses but lack the later, widespread activity associated with conscious access. From the global workspace perspective, masking prevents ignition. The initial signal never becomes strong or stable enough to enter the workspace, so it remains unconscious despite being processed. Another widely used paradigm is the attentional blink. When two targets are presented in rapid succession, awareness of the second often drops if it appears within a short time window after the first. The brain is already busy broadcasting the first target, leaving insufficient resources to ignite the second. Early sensory processing still occurs, but global access fails. These effects fit neatly with the idea of a limited capacity workspace. Only a small amount of information can be globally broadcast at any given moment. Neural data have provided partial support for this picture. In many studies, consciously perceived stimuli are associated with late, widespread patterns of brain activity involving frontal and parietal regions, while unconsciously processed stimuli show only early, local responses. However, this is where controversy enters. Those late, widespread signals often occur around the same time that a person prepares to report their experience. This raises a difficult question. Do these signals reflect consciousness itself, or do they reflect the act of reporting, deciding, and responding? This debate has become one of the central tensions surrounding global workspace theory. Supporters argue that global access is precisely what makes reporting possible. If information is being broadcast widely, then it should naturally engage decision-making and motor systems. Late activity is not a flaw of the theory, but a feature of what conscious access does. Critics counter that these signals may overestimate the neural footprint of experience itself. They argue that consciousness might arise earlier or more locally, and that late frontal activity reflects what happens after experience, not experience itself. This disagreement has motivated the development of no-report paradigms, where researchers attempt to identify neural signatures of conscious perception without requiring explicit report. Some findings suggest that certain aspects of conscious perception may occur without the full frontal ignition predicted by the strongest versions of the model. Other findings still support the need for widespread integration. What remains clear is that global workspace theory has helped sharpen the questions. It forces researchers to ask not just whether a stimulus is processed, but whether it becomes globally available. It encourages careful separation between early sensory activity, later decision-related activity, and the conditions under which information becomes flexible and shareable. The theory also makes specific predictions beyond perception. If consciousness is global access, then conscious information should interact strongly with memory systems. It should be more likely to be stored and retrieved. It should be easier to combine with past knowledge. Unconscious information, by contrast, should fade quickly or influence behavior only in narrow ways. Similarly, conscious contents should generalize across tasks. If you're aware of something, you should be able to use that information in many different contexts, not just the one that triggered it. This task generality is a hallmark prediction of the workspace idea. Global workspace theory also offers a natural way to think about changes in consciousness during sleep and anesthesia. When long-range communication breaks down, information may still be processed locally, but it fails to ignite. Experience fades, not because the brain stops working, but because information is no longer being shared widely enough to support awareness. At the same time, the theory is careful not to claim that global broadcasting explains everything. It does not pretend to solve the hard problem of why global access feels like something from the inside. It remains a functional account. It explains what consciousness does, not why doing that is accompanied by experience. This restraint is part of its strength. Global workspace theory does not insist that consciousness lives in a particular place. It does not claim that a single signal or region is the essence of awareness. It proposes a role that information can play within a complex system, and it asks whether that role lines up with what conscious experience seems to be like. The ongoing debate over late signals, report, and awareness shows that the theory is still under active refinement. Some versions emphasize frontal involvement more strongly. Others allow for more local ignition under certain conditions. Empirical results continue to push the model to become more precise. What global workspace theory has undeniably achieved is clarity. It has shifted the conversation from vague questions about where consciousness might be hiding, to concrete questions about information sharing, stability, integration, and flexibility. It has provided a framework that connects subjective experience to observable patterns without claiming more than the data can support. In doing so, it has helped turn consciousness from a philosophical puzzle into a disciplined scientific target, one that can be tested, challenged, and gradually constrained by evidence, even as its deepest mystery remains intact. Integrated information theory begins from a very different starting point than most scientific accounts of consciousness. Instead of asking what consciousness does, it asks what consciousness is like from the inside, and then works outward. The theory is most closely associated with Giulio Tononi, who proposed that if consciousness is real and measurable, it must have certain fundamental properties that are present in every conscious experience, regardless of content. These properties should not depend on what the brain is doing for survival or behavior, but on how experience itself is structured. The first of these properties is integration. Every conscious experience is unified. Even when many things are happening at once, the experience arrives as a single whole. Colours, sounds, thoughts, and bodily sensations do not appear as separate streams that need to be stitched together. They arrive already combined, as one moment of awareness. The second property is differentiation. Although experience is unified, it is also richly detailed. A single moment of consciousness can distinguish between countless possibilities. A scene can contain many colours, shapes, depths, and meanings, all at once. Experience is not a blur, it is specific. Integrated information theory, often shortened to IIT, takes these two features seriously. It argues that consciousness corresponds to the degree to which a system is both integrated and differentiated at the same time. To explain this in plain language, imagine two extremes. On one end, consider a system made of many independent parts that do not interact. Each part might process information, but nothing binds them together. Such a system lacks integration. According to IIT, it would not support unified experience. On the other end, imagine a system where all parts behave in lockstep, doing exactly the same thing at the same time. This system is integrated but not differentiated. It cannot represent many distinct possibilities. According to IIT, this too would lack rich experience. Consciousness in this framework arises when a system achieves both. Its parts must interact in a way that creates a unified whole while still allowing many distinct states. From this perspective, consciousness is not defined by input or output. It is not defined by behavior, report, intelligence, or usefulness. It is defined by intrinsic structure, by how the system is organized internally from its own point of view. This is one of the most radical aspects of the theory. IIT explicitly rejects the idea that consciousness depends on global broadcasting, task flexibility, or reportability. A system could be conscious even if it cannot speak, act, or communicate, as long as its internal structure meets the criteria. Conversely, a system could perform complex tasks and still lack consciousness if its internal organization is insufficiently integrated. To make this precise, IIT introduces a formal measure intended to capture integrated information. In technical work, this measure is often referred to by a Greek letter, but for voice-over clarity it can be described as the amount of information generated by the whole system that cannot be reduced to the sum of its parts. In other words, it asks how much the system's current state depends on interactions within the system, rather than on independent components acting alone. If removing or partitioning parts of the system drastically changes what the system can do internally, integration is high. If the system can be cleanly split into independent pieces without much loss, integration is low. According to IIT, the level of consciousness corresponds to the amount of integrated information present, while the specific structure of that integration corresponds to the quality of experience. This leads to a striking claim. Consciousness is not something the brain produces as a byproduct of computation. It is identical to a particular kind of causal structure instantiated by the brain. Experience is what that structure feels like from the inside. This view has unusual implications. For one, it suggests that consciousness is graded. Different systems may have different degrees of consciousness, depending on how integrated and differentiated they are. This opens the door to discussions about animal consciousness that do not rely on behavioral similarity to humans. Many animals have nervous systems that are highly integrated, even if they lack language or complex reasoning. At the same time, IIT places strong constraints on machine consciousness. A digital computer that processes information in a largely feed-forward, modular way might perform impressive tasks while generating very little integrated information. According to the theory, such a system could be functionally sophisticated and yet only minimally conscious, or not conscious at all. This is where IIT sharply contrasts with workspace accounts. Global workspace theory emphasizes what information can do. IIT emphasizes what information is. Both aim to explain the same phenomenon, but they carve it at very different joints. Despite its elegance, IIT is also one of the most controversial theories in consciousness science. One major challenge lies in measurement. Calculating integrated information precisely is computationally difficult, even for small systems. For large, realistic brains, exact calculation is currently impractical. Researchers rely on approximations and indirect measures, which raises questions about how confidently the theory can be tested. Another criticism concerns counterintuitive predictions. Because IT focuses strictly on internal structure, it can imply that some systems have consciousness when common sense strongly resists the idea. Certain highly integrated but simple systems could, in principle, have non-zero consciousness. At the same time, Some artificial systems that appear intelligent might score very low. Supporters argue that this discomfort reflects bias rather than error. Critics argue that it reveals a mismatch between the theory and lived experience. There are also debates about whether integration alone is sufficient. Some researchers argue that IIT underplays the role of dynamics, learning, and interaction with the environment. Others question whether intrinsic causal structure can be meaningfully separated from function in real biological systems. Empirical testing presents another difficulty. While IIT makes strong claims, translating those claims into decisive experiments has proven challenging. Correlations between measures of integration and levels of consciousness have been reported in contexts such as sleep, anesthesia, and brain injury. But alternative explanations remain possible. To its credit, IIT does not avoid these criticisms. Its proponents acknowledge the open problems and treat the theory as a work in progress rather than a finished answer. What IIT contributes most powerfully is a reframing of the question. It insists that any serious theory of consciousness must account for the structure of experience itself, not just its functional role. It challenges the assumption that consciousness exists only to enable reporting, planning, or communication. And it forces careful thinking about what it would actually mean for a system to have an inner life. Whether IIT turns out to be fundamentally correct, partially correct, or deeply flawed, it has already reshaped the conversation. It has pushed consciousness science to grapple with intrinsic properties rather than external behavior alone. In doing so, it highlights a quiet but important possibility: that consciousness may not be something added on top of physical systems, nor something that magically appears when tasks become complex enough, but something that depends on how a system is organized at its core. The debate over IIT remains unresolved. Measurement challenges persist, predictions continue to be tested, disagreements remain sharp, but the theory's value does not depend on immediate resolution. It lies in the way it expands the space of serious scientific options, reminding researchers that understanding consciousness may require not just better experiments, but a willingness to rethink what counts as explanation in the first place. Not every theory of consciousness agrees that awareness needs to be broadcast across the whole brain. Some accounts argue that experience can arise much closer to the sensory surface, through local interactions that never spread far enough to light up large networks at all. One of the most influential of these accounts is recurrent processing theory, most strongly associated with Victor Lamb. The starting point of recurrent processing theory is simple and deliberately modest. When a stimulus enters the brain, it does not arrive all at once as a finished perception. Information flows forward through a hierarchy of sensory areas. In vision, for example, early regions respond to basic features such as edges, orientation, and contrast. Later regions respond to more complex patterns like shapes, objects, and faces. This initial forward sweep happens very quickly and largely automatically. Signals move from one layer to the next in a mostly one-directional cascade. This is known as feed-forward processing. Feed-forward processing is powerful, but according to recurrent processing theory, it is not enough for conscious experience. The crucial step comes next. After the initial sweep, higher areas send signals back to earlier sensory regions. These feedback signals interact with the original input, refining it, stabilizing it, and embedding it in a local loop. This back-and-forth exchange is called recurrent processing. According to this view, consciousness arises when sensory representations become part of these recurrent loops. Awareness does not require information to be shared with decision systems, language systems, or motor planning areas. It requires the signal to echo, settle, and sustain itself within sensory cortex through feedback. This idea immediately challenges global broadcasting models. If recurrent processing is sufficient, then awareness can exist without widespread activation of frontal or parietal regions. Conscious experience could be vivid, detailed, and local, even if it never becomes globally available for report or deliberate control. To see why this matters, it helps to return to a familiar experimental tool: visual masking. In masking experiments, a stimulus is presented very briefly and then quickly followed by another stimulus that interferes with its processing. Even though the first stimulus reaches early visual areas, participants often report no awareness of it. From a recurrent processing perspective, this makes sense. The initial feed-forward sweep still occurs. Early sensory areas respond. Information is processed. But the mask disrupts the feedback signals before recurrent loops can form. Without recurrence, the representation never stabilizes into conscious experience. In this interpretation, masking does not prevent information from entering the brain. It prevents information from looping back. This fits neatly with timing data. Neural responses associated with feed-forward processing occur early and reliably, regardless of awareness. Signals associated with feedback and recurrence appear slightly later, and their presence or absence often tracks conscious perception more closely. Supporters of recurrent processing theory argue that this timing distinction is crucial. Consciousness is not about how much activity there is, nor how far it spreads, but about whether the right kind of interaction occurs within sensory systems. This leads to a striking prediction. Conscious experience can exist without reportability. If awareness depends on local recurrence rather than global access, then it is possible for someone to have a vivid experience that never reaches decision or language systems. The experience would be real from the inside but inaccessible from the outside. This idea resonates with several familiar phenomena. Dreams are one example. During dreaming, sensory cortex can be highly active and internally driven, producing rich visual and emotional experiences. At the same time, frontal systems involved in control, planning, and self-monitoring are often less engaged. Experience unfolds, but access is limited. Certain meditative or absorbed states offer another illustration. Attention may narrow, external responsiveness may drop, yet inner experience can remain intense and detailed, even difficult to describe afterward. Recurrent processing theory treats these cases not as special exceptions, but as natural outcomes of how awareness is generated. The theory also helps clarify why report is such a dangerous proxy for consciousness. If report requires global access, then any theory that equates consciousness with report will automatically exclude experiences that fail to reach that level, even if they are genuinely felt. This does not mean recurrent processing theory denies the importance of global interactions altogether. It simply assigns them a different role. Global broadcasting may be necessary for certain functions, such as deliberate decision-making, verbal report, and long-term planning. But those functions are not identical to experience itself. They build on awareness rather than create it. From this perspective, the brain contains multiple layers of processing. Feed-forward activity supports detection. Recurrent activity supports experience. Global access supports flexible use. Each layer adds capabilities, but they should not be confused. Critics of recurrent processing theory raise several objections. One concern is whether local recurrence is really sufficient. Some experiments show conscious perception without clear evidence of strong feedback within early sensory areas. Others suggest that frontal involvement may be more consistent than the theory allows. Another challenge comes from the difficulty of measuring recurrence directly. Feedback signals can be subtle, short-lived, and hard to separate from other processes. Much of the evidence relies on timing differences and indirect inference. There is also debate about whether recurrent processing alone can explain the unity and coherence of experience. Local loops might account for specific contents, but how those contents are bound together into a single moment of awareness remains an open question. Supporters respond that recurrence does not occur in isolation. Sensory areas are richly interconnected both within and across modalities. Local loops can still participate in larger patterns without requiring full global broadcast. Importantly, recurrent processing theory does not claim to be a complete explanation of everything conscious minds can do. It focuses on the minimal conditions for awareness to arise. Higher cognitive functions are treated as additions, not prerequisites. This minimalist stance is both its strength and its vulnerability. By lowering the bar for consciousness, the theory makes room for experiences that are private, fleeting, and inaccessible to report. At the same time, it risks being too permissive, attributing awareness in cases where intuition hesitates. What makes recurrent processing theory valuable is not whether it ultimately turns out to be the full story, but how it sharpens the questions. It forces researchers to distinguish between processing and experience, between access and awareness, and between what is measured and what is lived. It highlights the importance of feedback, timing, and local dynamics, rather than sheer scale. Most importantly, it reminds consciousness science of a simple possibility. That awareness might not require a grand announcement to the entire brain. It might begin quietly, in the subtle echo of signals talking back to themselves, long before any decision is made, any word is chosen, or any action is planned. In that sense, recurrent processing theory offers a humbler image of consciousness. Not as a spotlight sweeping across the mind, but as a pattern that settles just enough to be felt, even if it never asks to be noticed. Some theories of consciousness start with perception, others start with information sharing. Higher order theories take a different route entirely. They begin with a deceptively simple idea. Perhaps an experience becomes conscious only when the mind knows that it is having it. This family of views is often grouped under the label higher order theories, and one of the most influential versions is higher order thought theory, most closely associated with David Rosenthal. The core claim is not that experience itself is special, but that awareness of experience is. According to higher order thought theory, a mental state such as seeing a color or feeling a sensation can occur without being conscious. What makes it conscious is the presence of a higher order representation that targets that state. In other words, the mind not only has an experience, but also represents itself as having that experience. The experience is the first order state. The awareness of having the experience is the higher order state. Consciousness, on this view, is not just perception, it is perception plus self-representation. This distinction may sound abstract, but it reflects something familiar. There are moments when something happens in the mind without being noticed, and then moments when it becomes noticed. A sound plays in the background, unnoticed, until attention snaps to it, and it suddenly becomes vivid. A thought drifts by, half-formed, until it is recognized as a thought and can be examined. Higher order theories propose that this recognition is not just attention, but a specific kind of mental representation. The mind forms a thought about its own state. That thought does not need to be verbal or deliberate. It does not need to involve introspection in the everyday sense. It simply needs to represent the first order state as occurring. Importantly, The higher order state is not the same as reflection or analysis. You do not need to think about thinking in a philosophical way. The representation can be automatic, vast, and unconscious in itself. What matters is that it targets another mental state. This idea creates a clean separation between mental states and conscious mental states. A visual system might process information about light, edges, and motion. That processing can guide behavior. But until the system also represents itself as being in that state, the experience remains unconscious. This allows higher order theories to explain why some mental processes feel invisible from the inside. The brain can do a great deal without generating higher order representations about what it is doing. One of the strengths of this framework is that it naturally connects consciousness to metacognition. Metacognition refers to the ability to monitor and evaluate one's own mental states. Confidence judgments are a common example. When you answer a question and also have a sense of how sure you are engaging in metacognitive assessment. Higher order theories suggest that confidence is not an extra layer added on top of consciousness. It is closely related to the very mechanism that makes a state conscious in the first place. Representing yourself as being in a particular mental state opens the door to evaluating that state. This connection has made higher order theories attractive to researchers studying confidence, error awareness, and self-monitoring. Experiments show that people can sometimes perform tasks accurately while having little insight into how well they are doing. In other cases, performance and confidence track closely together. From a higher order perspective, these differences reflect variation in higher order representations rather than variation in first order processing. This brings the discussion to a particularly important clinical phenomenon: blind sight. Blind sight occurs in individuals with damage to primary visual cortex. These individuals report being blind in part of their visual field. They insist that they see nothing there, and yet, when forced to guess, they can often discriminate shapes, movements, or locations at rates well above chance. Information is clearly being processed, behavior is being guided. But the person reports no visual experience. Blindsight poses a serious challenge for any theory that equates consciousness with sensory processing alone. Higher order theories offer a straightforward interpretation. The first order visual representations are still present and functional, but the higher order representations that would make those states conscious are missing or disrupted. The person sees, in a technical sense, but does not know that they see. This distinction allows higher order theories to explain how perception without awareness is possible, without denying the integrity of the subjective reports. The person is not confused or mistaken. The higher order representation simply never forms. Similar logic can be applied to other dissociations. People can respond to emotional stimuli without consciously feeling the emotion. They can adjust behavior based on information they cannot report. In each case, first-order processing may be intact while higher-order awareness is absent. Another appealing feature of higher-order theories is that they offer a clear account of the difference between conscious and unconscious mental states without relying on global broadcasting or specific neural locations. Consciousness depends on a relation between states, not on scale or spread. However, this strength is also a source of controversy. One criticism is that higher-order theories risk explaining consciousness by adding an extra layer rather than illuminating the original phenomenon. Saying that an experience becomes conscious when there is a thought about it may seem to shift the mystery rather than resolve it. Why does the higher-order thought make a difference? Why does representing a state suddenly give it a subjective feel? Supporters respond that the theory does not aim to explain why consciousness exists at all, but to explain what distinguishes conscious from unconscious mental states within a functioning system. In that sense, it is a theory of access to awareness rather than of phenomenology itself. Another debate concerns whether higher-order representations are always necessary. Some experiments suggest that conscious experience can occur even when metacognitive access is weak. For example, people can sometimes have vivid perceptual experiences while being poor at judging their own performance or confidence. Higher-order theorists argue that metacognition as measured in experiments may not capture all forms of higher-order representation. The relevant representations may be simpler, faster, and less accessible to report than confidence judgments suggest. There are also questions about neural implementation, where and how are higher-order representations generated. Some proposals emphasize frontal brain regions involved in monitoring and control. Others allow for more distributed mechanisms. Empirical evidence remains mixed, and the theory continues to evolve in response to data. Despite these debates, higher-order theories make a valuable contribution by foregrounding the role of self-representation. They highlight that consciousness is not just about what the brain processes, but about what the system takes itself to be doing. Awareness, on this view, is inseparable from a minimal form of self-knowledge. This does not mean that consciousness requires a narrative self, a personality, or a sense of identity. The self involved here is thin. It is simply the system representing its own states as its own. That thinness is important. It allows higher-order theories to apply to animals, infants, and perhaps artificial systems, without requiring language or reflection. The question becomes whether the system can represent its own internal states, not whether it can talk about them. In this way, higher-order theories act as a bridge between raw experience and the sense of self. They suggest that consciousness may emerge not when information is processed, nor when it is shared widely, but when the mind turns back on itself just enough to register that something is happening. Whether this is the whole story remains an open question, but by drawing attention to awareness of awareness, higher-order theories sharpen one of the most intriguing possibilities in consciousness science. That what makes an experience conscious may not be how vivid it is or how widely it spreads, but the quiet fact that the system knows it is having it at all. Perception feels immediate and effortless. Light hits the eyes, sound reaches the ears, and the world simply appears. It feels as though the brain is passively receiving information and turning it into experience, like a camera pointed outward. Predictive processing turns that picture upside down. According to this framework, the brain is not primarily a device for recording the world, it is a device for predicting it. Experience is not built from the outside in, but from the inside out, with sensory input serving mainly to correct the brain's expectations. One of the most influential figures associated with predictive processing is Carl Friston, whose work helped formalize the idea that the brain operates as a prediction machine at every level of processing. The basic claim is straightforward. At any moment, the brain carries models of what it expects to encounter. These models generate predictions about incoming sensory signals. When actual input arrives, it is compared against those predictions. Any mismatch produces an error signal, which is then used to update the model. Over time, this constant loop of prediction and correction allows the brain to maintain a stable and coherent experience of the world, even though the sensory data themselves are noisy, incomplete, and ambiguous. This process happens continuously and largely outside awareness. The reason the world feels stable is not because sensory input is perfect, but because the brain actively fills in gaps, smooths over inconsistencies, and resists change unless the evidence is strong enough to force an update. This can be seen in everyday perception. Vision does not flicker or collapse when you blink, even though sensory input briefly disappears. Sounds remain coherent despite echoes and background noise. Objects retain their identity as lighting conditions change. Predictive processing explains this stability by treating perception as inference. The brain infers the most likely causes of its sensory input, given prior knowledge and current context. Sensory data constrain those inferences, but they do not dictate them outright. Illusions offer a clear window into this process. In many visual illusions, the sensory input is fixed, yet perception changes depending on context, expectation, or prior exposure. Lines appear bent, colors shift. Motion is perceived where none exists. These effects are not failures of perception. They are the brain doing exactly what it evolved to do, making its best guess under uncertainty. From a predictive perspective, perception is a controlled hallucination, anchored by sensory input but shaped by expectation. Most of the time, the hallucination is accurate enough that it feels like direct contact with reality. This framing becomes especially powerful when considering ambiguous or degraded stimuli. When information is sparse, predictions carry more weight. When input is clear and strong, predictions are constrained tightly. This balance helps explain why hallucinations and illusions become more likely when sensory input is unreliable, such as in darkness, isolation, or certain altered states. When bottom-up signals weaken, top-down expectations can dominate. Predictive processing also offers a natural explanation for why perception feels effortless. If the brain were constantly building experience from scratch, perception would be slow and demanding. By relying on predictions, the system can operate efficiently, updating only when necessary. So where does consciousness fit into this picture? Predictive processing is not a theory of consciousness in the narrow sense. It does not specify exactly what makes a prediction conscious rather than unconscious. Instead, it provides a framework for understanding how perceptual content is generated in the first place. Experience, on this view, is the brain's best current model of the causes of its sensory input. What you consciously experience is not raw data, but a prediction that has survived error correction well enough to remain stable. This idea connects naturally to the sense that perception is constructive rather than passive. Colors, shapes, sounds, and even bodily feelings are not copied directly from the world. They are inferred. Predictive processing also blurs the boundary between perception and imagination. Both involve the brain generating models. The difference lies in how strongly those models are constrained by sensory evidence. When constraint weakens, internally generated content can feel increasingly real. This prepares the ground for understanding hallucinations, dreams, and certain psychiatric conditions, where the balance between prediction and correction shifts. However, predictive processing also faces important limitations as a theory of consciousness. First, prediction alone does not explain why some inferred content is experienced and other inferred content remains unconscious. The brain makes countless predictions about posture, heart rate, and motor control that never enter awareness. Prediction is ubiquitous, consciousness is not. Second, the framework risks becoming too general. If every brain process can be described as prediction and error correction, then the theory explains everything and nothing at the same time. Without additional constraints, it struggles to specify what distinguishes conscious inference from unconscious regulation. Third, predictive processing does not by itself resolve the question of subjective experience. It explains how content is generated and stabilized, but not why that content is accompanied by feeling. It describes the mechanics of construction, not the origin of phenomenology. Supporters acknowledge these limits. Predictive processing is best understood as a unifying account of perception and cognition, rather than a standalone answer to the problem of consciousness. It describes the stage on which consciousness plays out, not necessarily what turns the lights on. Where the framework shines is in its explanatory reach. It unifies perception, action, learning, and expectation under a single principle. It explains why perception is robust yet flexible, why illusions are systematic rather than random, and why the brain is so sensitive to context. It also offers a powerful way to think about altered experience. Changes in consciousness can be understood as shifts in the balance between prediction and correction, rather than as mysterious malfunctions. At the same time, predictive processing must be paired with other theories to address the full picture. It tells us how experience is shaped, but not when or why it becomes conscious. That question remains open. What predictive processing contributes most strongly is a reframing. Experience is not a window opened onto the world. It is a model maintained by the brain, constantly adjusted, quietly negotiated, and usually good enough to keep you oriented. Consciousness, within this view, is not about receiving reality, but about actively making sense of it, moment by moment, under conditions of uncertainty. That insight does not solve the mystery of awareness, but it changes the way the mystery is approached, grounding it in inference, expectation, and the remarkable fact that the brain is always guessing, and usually guessing well enough that the guesses feel like reality itself. Attention and consciousness are often spoken about as if they were the same thing. They are not. They overlap, interact, and influence one another constantly. But they can also come apart in surprising ways. Untangling that relationship is essential for interpreting almost every experiment in consciousness science. Attention refers to the selective allocation of processing resources. It is the brain's way of prioritizing certain information over others. Consciousness, by contrast, refers to subjective experience itself, the felt presence of sights, sounds, thoughts, or sensations. In everyday life, attention and awareness usually travel together, which is why they're so easy to confuse. When attention is focused, experience often feels clearer. When attention drifts, experience can feel faint or fragmented. But this coupling is not perfect, and the cracks reveal something important. One of the clearest demonstrations comes from inattentional blindness. In classic experiments, participants are asked to focus on a demanding task, such as counting passes between players on a screen. While their attention is occupied, an unexpected object appears in plain view. Many participants fail to notice it entirely. They look straight at it, yet report no experience of seeing it. The striking part is not that attention was elsewhere. It is that without attention, awareness itself seems to vanish. The object leaves no memory trace and no subjective impression. Change blindness reveals a related effect. When a scene alternates with brief interruptions, large changes can go unnoticed if attention is not directed toward them. Buildings disappear. Colors shift. People swap places. Without attention, awareness does not automatically update. These findings show that attention is often necessary for stable, reportable awareness. But necessity in one direction does not imply identity. There is also strong evidence for attention without awareness. In many experiments, attention can be directed to stimuli that never enter conscious experience. For example, a participant may be cued to attend to a location where a stimulus is presented below the threshold of awareness. Brain activity and behavioral effects show that attention enhances processing at that location, even though the participant reports seeing nothing. Attention can improve discrimination, speed responses, and bias decisions, all without producing a conscious percept. The brain prioritizes information that remains unseen. There's also evidence for awareness without focused attention. Some experiences seem to arise even when attention is weak or diffuse. Background sensations, ambient sounds, and the general sense of presence often persist without deliberate focus. In some cases, stimuli can be consciously perceived even when attention is directed elsewhere, especially if they are strong or emotionally salient. These dissociations make it clear that attention and consciousness are distinct processes that interact but do not define one another. This distinction matters deeply for experimental interpretation. If a brain signal changes when attention shifts, is it tracking attention, awareness, or both? If awareness disappears when attention is withdrawn, is attention the cause of awareness or simply a stabilizing factor that makes awareness durable and reportable? Different theories answer these questions in different ways. Some accounts treat attention as a gatekeeper that allows information to become conscious. Others treat attention as a modulator that shapes conscious content without creating it. Still others argue that attention and awareness arise from partially independent mechanisms that happen to align most of the time. A particularly interesting attempt to clarify this relationship comes from attention schema theory, proposed by Michael Graciano. Attention schema theory begins with a functional observation. The brain needs to control attention efficiently. To do that, it benefits from having an internal model of what attention is doing. Just as the brain maintains a body schema to track the body's position, it may maintain an attention schema to track its own attentional state. According to this theory, awareness is the brain's simplified model of attention. The model is not detailed or mechanistic. It does not represent neurons or signals. Instead, it provides a coarse, user-friendly description, something like a sense that attention is being directed toward an object, accompanied by the feeling that the object is being experienced. On this view, consciousness is not a mysterious extra property added to attention. It is the brain's internal narrative about its own attentional processes. This helps explain why awareness feels intangible and hard to pin down. The attention schema leaves out details about implementation, just as the body schema leaves out information about muscles and nerves. What remains is a useful summary, not a literal description. Attention schema theory also offers an explanation for why people readily attribute consciousness to others. The same modeling machinery used to track one's own attention can be applied outward, allowing the brain to infer that other agents have awareness too. Consciousness becomes something attributed, both inwardly and outwardly. Importantly, the theory does not claim that attention and awareness are identical. Attention is a real process that allocates resources. Awareness is the model of that process. This allows for dissociations. Attention can operate without a strong model, and awareness can sometimes be generated even when attentional control is degraded. The theory also helps explain why awareness is so closely linked to report and self-description. If awareness is a model used for control and communication, then it makes sense that it is accessible to language and introspection, even if it does not reflect the full underlying complexity. Critics raise familiar concerns. Some argue that modeling attention does not explain why experience feels like anything at all. Others question whether awareness can be reduced to a description without leaving something essential out. Still, others point out that attention itself is multifaceted, and modelling one aspect may not capture the richness of experience. Supporters respond that the theory does not aim to solve the deepest metaphysical questions. It aims to explain why awareness behaves the way it does, why it is tied to attention yet separable, and why it has the features it does. Regardless of where one stands, the distinction between attention and consciousness has reshaped experimental design. Researchers now take care to manipulate attention and awareness independently where possible. They design tasks that hold one constant while varying the other. They interpret brain signals with greater caution, aware that attentional effects can masquerade as markers of consciousness. This has led to a more disciplined field. Attention is no longer treated as a synonym for awareness. Consciousness is no longer assumed to follow automatically from focus. Instead, their relationship is treated as a dynamic interaction, one that can strengthen, weaken, or fracture depending on context. The result is a clearer picture. Attention selects, awareness presents. Sometimes they align, sometimes they part ways. Understanding where and why they diverge does not dissolve the mystery of consciousness, but it sharpens it. It replaces vague assumptions with testable distinctions, and it reveals that even the most familiar features of the mind can pull apart under careful scrutiny. In that separation, consciousness science gained something valuable, not certainty but clarity. For most of everyday life, consciousness feels unified. There is one point of view, one stream of experience. Thoughts, sensations, and intentions all seem to belong to a single self. That unity feels so natural that it is easy to assume it must be fundamental. Split brain research challenges that assumption in one of the most direct ways science has ever managed. The story begins with a surgical procedure developed in the mid-20th century to treat severe drug-resistant epilepsy. In some patients, seizures spread uncontrollably from one hemisphere of the brain to the other. To limit that spread, surgeons cut the corpus callosum, the massive bundle of nerve fibers connecting the left and right hemispheres. This procedure became known as split brain surgery. One of the central figures in studying its consequences was Roger Sperry, who realized that these rare patients offered a unique window into how the brain supports unified experience. By carefully designing experiments that delivered information to only one hemisphere at a time, researchers could observe what happened when the brain's major communication highway was severed. The basic setup relied on a simple fact about brain organization. Each hemisphere primarily processes information from the opposite side of space. Information presented to the right visual field initially goes to the left hemisphere. Information presented to the left visual field goes to the right hemisphere. In an intact brain, the hemispheres quickly share what they receive. In a split brain, that sharing is dramatically reduced. The results were startling. When information was presented to the left hemisphere, patients could usually describe it verbally. The left hemisphere in most people supports language production. When a word or image appeared on the right side of space, the person could say what it was. But when information was presented to the right hemisphere, something different happened. The patient often reported seeing nothing, and yet their behavior told a different story. They could point to the correct object, select it with their left hand, or respond in ways that showed the information had been processed. The right hemisphere knew something the speaking left hemisphere did not. Further work by Michael Gazzaniga expanded these findings and revealed even richer dissociations. In some cases, the right hemisphere could follow simple instructions, make choices, and express preferences, all without access to language. The left hemisphere, meanwhile, would sometimes invent explanations for actions it did not initiate, creating a coherent narrative after the fact. This led to the idea of an interpreter function in the left hemisphere, a system that constantly tries to make sense of behavior and experience, even when it lacks full information. The interpreter is not lying. It is doing what brains do best, constructing a plausible story. These observations force an uncomfortable question. If each hemisphere can process information independently, can each have its own conscious experience? In other words, does split brain surgery create two streams of consciousness within one skull? Some researchers have argued that it does. On this view, the severed connection allows two semi-independent conscious systems to coexist. Each hemisphere has its own perceptions, intentions, and experiences, even if only one can speak. The unity of consciousness from this perspective is not guaranteed by biology alone. It depends on integration. Other researchers are more cautious. They point out that split-brain patients do not behave like two fully independent people. The hemispheres still share information through subcortical pathways. The person does not report feeling divided in everyday life. Conscious experience may remain largely unified, with dissociations appearing only under carefully controlled experimental conditions. There is also debate about how much consciousness the right hemisphere supports on its own. While it can process information and guide behavior, its experiences may be more limited, less reflective, or less integrated than those of the left hemisphere. The absence of language complicates interpretation. Just because an experience cannot be reported does not mean it is absent, but it also makes strong claims difficult to verify. What split brain research undeniably shows is that unity of consciousness is not automatic. When communication between brain regions is disrupted, experience can fragment in subtle and sometimes dramatic ways. Information that would normally be shared becomes isolated. Awareness in one part of the system can be cut off from awareness in another. This has important implications for theories of consciousness. For theories that emphasize integration, split brain cases serve as a direct test. If consciousness depends on information being integrated across the brain, then cutting major integrative pathways should alter the structure of experience. The observed dissociations fit naturally with that expectation. For global workspace accounts, the findings raise questions about how many workspaces might exist and how they interact. If global availability is required for conscious access, then severing connections may result in multiple smaller workspaces rather than one unified one. For higher-order theories, split-brain cases invite questions about self-representation. Does each hemisphere form higher-order representations of its own states? Does the sense of self fragment, even if the person does not notice? There is no single agreed answer, and that uncertainty is part of the value of the data. Split-brain research does not neatly resolve the problem of unity. Instead, it exposes the assumptions that theories make about what unity means and how it is achieved. It also highlights a deeper point. The feeling of being one conscious self is an achievement, not a given. It depends on communication, coordination, and integration across distributed systems. When those systems are altered, the feeling can change in ways that are surprising and deeply informative. In everyday life, the brain works hard to present a seamless picture. Conflicts are resolved quietly. Inconsistencies are smoothed over. Gaps are filled in. The result is a stable sense of being a single subject of experience. Split brain surgery peels that illusion back just enough to reveal the machinery underneath. What emerges is not chaos but structure. Different systems can support different kinds of awareness. Language, perception, action, and interpretation can come apart without the person falling apart. Consciousness proves to be more flexible, and more fragile than intuition suggests. These cases do not show that consciousness is easily divided. They show that its unity depends on how the brain is connected, and in that dependence lies a powerful lesson. Consciousness is not a simple light that switches on or off. It is a pattern maintained by cooperation. When the lines of communication change, the pattern changes too, revealing that even the most intimate feature of mental life is shaped by structure, not magic. Split brain research leaves the deepest question open. Is there one consciousness or two? What it makes clear is that the answer depends less on intuition and more on how minds are physically and functionally bound together, moment by moment inside the brain. One of the most powerful ways to understand consciousness is to watch what happens when it breaks, not all at once, but selectively. Certain neurological conditions reveal something deeply counterintuitive. Large amounts of information can still be processed by the brain, guide behavior, and influence decisions, even when conscious experience itself is partially or entirely absent. These cases force a clear separation between information and awareness. One of the most striking examples is hemispatial neglect. Hemispatial neglect typically follows damage to the right side of the brain, often involving parietal regions that play a role in spatial processing and attention. After such damage, patients may behave as if the left side of space no longer exists. This is not a problem with vision in the usual sense. The eyes and early visual pathways often function normally. Instead, the issue lies in awareness. A person with left-sided neglect may eat food only from the right side of a plate, shave only the right side of the face, or bump into objects on the left without reacting. When asked to describe a room, they may mention only items on the right. When asked to draw a clock, they may crowd all the numbers onto one side. What makes neglect especially revealing is that the missing side of space is not merely ignored. It is often actively denied. If asked whether anything exists on the left, patients may insist that nothing is there. The left side is not experienced as empty or dark. It is simply not part of experience at all, and yet processing continues. In some experiments, stimuli presented to the neglected side influence behavior in subtle ways. A word shown on the left may prime responses to related words shown later on the right. An image of a house with flames on the neglected side may cause discomfort or avoidance, even though the patient denies seeing anything unusual. The brain registers the information. The person does not experience it. This dissociation demonstrates that sensory processing alone is not enough for awareness. Information can be analyzed, categorized, and used without entering conscious experience. Neglect also shows that awareness is not evenly distributed across the brain. Damage to certain regions does not dim experience globally. It selectively removes access to specific contents, in this case, a portion of space. This selectivity is crucial for theories of consciousness. If consciousness was simply a matter of overall brain activity or general alertness, neglect would be difficult to explain. The patient is awake, responsive, and cognitively capable, yet entire classes of information fail to appear in experience. Blindsight provides a different but equally revealing window into partial awareness. Blindsight occurs after damage to primary visual cortex, often due to stroke or injury. Patients report being blind in part of their visual field. They insist that they see nothing there, and subjectively they are telling the truth. Yet when forced to guess, they can often discriminate features such as motion, orientation, or location at rates far above chance. They can point to where a stimulus appeared. They can detect movement. They can avoid obstacles placed in their blind field, but they deny having any visual experience. Blindsight is not about guessing cleverly or responding to subtle cues. performance remains above chance even when feedback is removed and confidence is low. The information is genuinely processed, but it does not give rise to visual awareness. This phenomenon challenges any account that equates consciousness with sensory representation alone. Visual information reaches the brain, it influences behavior, it guides action, and yet it does not feel like seeing. From the perspective of neural correlates of consciousness, blindsight raises a critical issue. Which neural activity reflects experience and which reflects processing without experience? Early visual responses can still occur in blindsight patients. Subcortical pathways and secondary visual areas remain active. But something essential is missing. The patterns of activity associated with conscious vision in intact individuals do not appear. This suggests that not all visual processing contributes equally to awareness. Some pathways support behavior without experience. Others are required for experience to arise. Neglect and blindsight together reveal a consistent pattern. Awareness can be lost in a content-specific way. The brain does not simply turn consciousness on or off. It loses access to particular kinds of information while preserving others. This has important consequences for how neural data are interpreted. Suppose a brain signal correlates with successful discrimination or accurate behavior. That does not guarantee it correlates with conscious experience. As blindsight shows, behavior can be supported by neural activity that never enters awareness. Similarly, a signal that disappears when awareness disappears may still reflect downstream consequences rather than experience itself. In neglect, some processing survives, even though awareness does not. These cases place strong constraints on what can count as a genuine neural correlate of consciousness. A candidate correlate must track subjective experience, not just information processing or task performance. It must disappear when experience disappears, even if behavior remains. This is why neglect and blindsight are so valuable. They provide natural experiments in which awareness and processing are pulled apart. They also complicate simple interpretations of attention. In neglect, attention is severely disrupted for one side of space. But the problem is not merely attentional. Even when attention is drawn to the neglected side through cues or instructions, awareness often fails to return. In blindsight, attention can be directed to the blind field, and processing can improve, yet awareness still does not emerge. These patterns suggest that attention can modulate processing without necessarily generating experience. Awareness requires something more. From a theoretical standpoint, these conditions challenge overly broad theories. Any account that claims consciousness arises wherever information is processed must explain why so much processing remains unconscious in these cases. Any account that ties awareness tightly to behavior must explain why behavior persists without experience. Neglect and blindsight instead support the idea that consciousness depends on specific patterns of integration, recurrence, or self-representation, not just activity or performance. They also highlight the importance of asking patients about their experience, not just measuring what they can do. In neglect, patients are not confused about what they experience. Their reports are consistent and sincere. In blindsight, patients genuinely insist they see nothing. Treating these reports as mere errors would miss the point entirely. Subjective reports, while imperfect, are essential for identifying when awareness is present or absent. Without them, these dissociations would be invisible. There is also a broader lesson here. Consciousness is not required for many forms of intelligent behavior. The brain can classify, decide, and act without awareness in surprising ways. Awareness appears to be something added, not something automatic. This does not make consciousness useless. it makes it selective. Awareness may be especially important for flexible reasoning, long-term planning, learning from novel situations, and integrating information across domains. But it is not needed for every operation. Neglect and blindsight also remind us that consciousness is vulnerable. Small changes in brain structure can profoundly alter what appears in experience. Entire regions of reality can vanish without the person feeling that anything is missing. This vulnerability is unsettling, but scientifically invaluable. By studying where and how awareness fails, researchers gain clues about what normally sustains it. Absence becomes a guide to presence. For neural correlates research, the implication is clear. Signals that survive in neglect and blindsight cannot, on their own, explain conscious experience. Signals that vanish when awareness vanishes deserve closer attention. But even here, caution is required. No single signal is likely to be the whole story. Consciousness appears to depend on relationships between signals, on patterns of interaction rather than isolated activity. Neglect and blindsight do not point to a simple location or mechanism. They point to a network of conditions that must be satisfied for experience to arise. What they offer instead is something more valuable. They show that consciousness is not identical to seeing, hearing, or thinking in a technical sense. It is not guaranteed by processing alone. It is a specific mode of operation, one that can fail selectively and silently. In revealing that separation, these conditions anchor the science of consciousness in hard clinical reality. They remind us that awareness is something the brain achieves, not something it cannot avoid, and in doing so, they reinforce a central theme. Information can exist without experience. Experience requires something more. Sleep provides one of the clearest demonstrations that consciousness does not depend on incoming sensory information. When the eyes are closed, muscles are still, and the outside world is largely cut off, experience does not necessarily vanish. Instead, it often turns inward, producing scenes, narratives, emotions, and sensations that can feel just as vivid as waking life. To understand how this is possible, it helps to start with the basic structure of sleep. Sleep is not a uniform state. It unfolds in cycles, moving through distinct stages characterized by different patterns of brain activity. Broadly speaking, these stages are divided into non-rapid eye movement sleep and rapid eye movement sleep. Non-rapid eye movement sleep includes lighter stages where awareness fades gradually, as well as deeper stages where responsiveness drops sharply, and experience is often minimal or absent. In these deeper stages, people are difficult to wake, and reports of experience are sparse, fragmented, or entirely missing. Rapid eye movement sleep is different. During this stage, the brain becomes highly active, especially in sensory and emotional regions. The eyes move rapidly beneath closed lids. Muscles are largely paralyzed to prevent acting out dreams, and consciousness often returns in a striking form, dreaming. Dream experiences can include detailed visual scenes, complex social interactions, strong emotions, and a continuous sense of being immersed in a world. They can unfold with a narrative structure, even though logic and physical laws are often distorted. The key point is that these experiences arise without direct sensory input. The brain generates them internally. This makes dreaming a powerful natural experiment. If consciousness required continuous input from the senses, dreams should not exist. If consciousness required constant interaction with the environment, sleep should be a blackout. Instead, awareness proves capable of persisting, changing, and sometimes flourishing when the brain is largely cut off from the outside. Neuroscientific studies of sleep have helped clarify what changes and what remains. During rapid eye movement sleep, activity in sensory cortex can resemble waking perception, even though no external signals are arriving. At the same time, activity in frontal regions involved in executive control and self-monitoring is often reduced. This combination helps explain why dreams feel vivid but bizarre, immersive but poorly regulated. Emotional centers, including areas involved in fear and reward, can be highly active. This contributes to the intense emotional tone of many dreams. Memory systems also play a role, recombining fragments of past experience into novel configurations. Dreaming consciousness therefore shares some features with waking awareness and lacks others. It has content, richness, and a sense of presence, but it often lacks reflective insight, stable identity, and deliberate control. The experience unfolds, but the dreamer usually accepts it without question. This makes dreams especially relevant for theories of consciousness. They show that global access, language, and executive control are not required for experience itself. Awareness can exist in a more constrained, locally generated form. At the same time, the altered balance of brain activity shows how different components contribute to the quality of experience. One particularly intriguing variation on dreaming consciousness is lucid dreaming. In lucid dreams, the dreamer becomes aware that they are dreaming while the dream continues. This awareness can range from a fleeting realization to a stable state in which the dreamer can reflect, remember waking life, and sometimes even influence the dream. Lucid dreaming provides a rare case where metacognition appears within sleep. The dreamer knows that the experience is an experience. That knowledge changes the structure of the dream. Emotional reactions often soften. Impossible events are recognized as impossible. A sense of agency may increase. Neuroscientific studies suggest that lucid dreaming involves partial re-engagement of frontal regions associated with self-monitoring and control, while the brain remains in a rapid eye movement sleep state. The dream does not end. Instead, a layer of awareness is added. This makes lucid dreaming especially valuable for studying the relationship between consciousness and self-awareness. It shows that reflective insight is not all or nothing. It can appear within an otherwise altered state. Sleep research has been shaped by decades of work from major institutions, including National Institutes of Health and the Max Planck Institute for Human Cognitive and Brain Sciences, which have supported large-scale studies of sleep physiology, dreaming, and memory. Their findings have helped establish that sleep is an active, organized process, not a passive shutdown. One consistent result is that consciousness during sleep is highly variable. Some nights include long stretches of vivid dreaming. Others pass with little remembered experience. Even within a single night, awareness can fade, return, fragment, and reassemble. This variability reinforces an important point. Consciousness is not tied to a single brain state. It does not appear only when the brain looks awake. It can emerge under different configurations, as long as certain conditions are met. At the same time, sleep also shows where consciousness fails. During deep, non-rapid eye movement sleep, reports of experience often drop dramatically. Brain activity becomes more synchronized and less differentiated. Communication between regions changes. The conditions that support rich experience appear to weaken. This contrast between dreaming and dreamless sleep provides a natural gradient for studying consciousness. By comparing brain activity across stages, researchers can look for patterns that track the presence or absence of experience, rather than wakefulness alone. Sleep also highlights the limits of external measurement. Dreaming consciousness is known primarily through report after waking. The experience itself is private, yet consistent patterns emerge across many individuals and cultures. People report similar features, similar distortions, and similar emotional themes. This convergence suggests that subjective reports, when handled carefully, can provide reliable data. At the same time, forgetting is common. Many dreams leave no trace. This reminds us that experience and memory are not the same. Consciousness can occur without leaving a durable record. Sleep therefore sharpens several themes that run through consciousness science. Awareness does not require sensory input. Awareness does not require deliberate control. Awareness does not guarantee memory. What it does require appears to be a particular mode of brain organization, one that can arise in waking life, dreaming, and possibly other altered states. Dreams also serve as a gentle warning against overly narrow theories. Any account that insists consciousness must involve active engagement with the world struggles to explain dreaming. Any account that equates awareness with rational self-control struggles to explain the emotional and illogical richness of dreams. Sleep shows that consciousness is flexible. It can withdraw from the world and build one of its own. It can loosen its rules and still feel real. It can operate under conditions that look, from the outside, like disconnection. In doing so, sleep and dreaming remind us of something quietly profound. Consciousness is not merely a response to the world. It is an activity the brain can sustain on its own, shaping experience even when the senses fall silent. That insight sets the stage for understanding what happens when consciousness is altered more dramatically still, not by sleep but by the deliberate suspension of awareness itself. Anesthesia offers something rare in the study of consciousness, a reliable, repeatable way to make experience disappear. Unlike sleep, which drifts in and out unpredictably, general anesthesia allows clinicians to switch consciousness off deliberately, maintain that state for hours, and then allow it to return. From a scientific perspective, this makes anesthesia an unusually powerful tool. It places strong causal constraints on any theory that claims to explain awareness. If a theory of consciousness is correct, it must be able to explain what anesthesia removes, how it removes it, and why experience vanishes even while much of the brain remains active. General anesthesia is not a single substance or a single mechanism. It is a class of drugs with different molecular targets that converge on a similar outcome: the loss of conscious experience. Some anesthetic agents enhance inhibitory signaling in the brain, particularly through systems that dampen neural activity. Others interfere with excitatory communication, making it harder for neurons to influence one another. Still others alter how information flows across networks rather than simply silencing activity. What matters most is not that the brain shuts down completely. It does not. Under general anesthesia, the brain continues to consume energy. Neurons continue to fire. Sensory signals may still reach early processing stages. Reflexes can remain intact. Yet subjective experience disappears. Patients do not feel pain. They do not form memories. They do not experience time passing. From the inside, there is nothing at all. This immediately tells us something important. Consciousness is not equivalent to overall brain activity. If it were, anesthesia would require near-total neural silence. Instead, it selectively disrupts the conditions under which activity becomes experience. One of the most consistent findings in anesthesia research is the breakdown of large-scale communication. Studies using brain recording and imaging techniques show that as anesthesia deepens, long-range interactions between distant regions weaken. Signals become more local. Information that would normally propagate across the brain becomes trapped in smaller circuits. At the same time, patterns of activity grow more regular and less complex. Instead of rich, flexible dynamics, the brain begins to show repetitive rhythms and synchronized bursts. Different regions start to behave more similarly, losing the differentiated patterns seen in conscious states. This reduction in complexity has been a major focus of research. In conscious states, brain activity tends to be both integrated and differentiated. Many regions interact, but they do not all do the same thing at the same time. Under anesthesia, that balance collapses. Either integration is lost, or differentiation is reduced, or both. From the perspective of theories like integrated information theory, this collapse is especially significant. Reduced integration and reduced differentiation would predict reduced consciousness, which matches clinical observation. From the perspective of global workspace accounts, anesthesia appears to prevent information from being broadcast widely. Local processing may continue, but global availability fails. From the perspective of recurrent processing theories, feedback loops may be disrupted or rendered unstable, preventing sensory representations from sustaining awareness. The striking point is that very different drugs, acting on different molecular targets, produce similar effects at the network level. This convergence suggests that consciousness depends less on specific chemicals and more on patterns of interaction. Clinical research has played a crucial role in uncovering these effects. Much of what is known about anesthesia and consciousness comes from work supported by organizations such as the American Society of Anesthesiologists, which promotes large-scale studies of brain function during surgery. Research funded through hospitals and medical centers worldwide has helped establish that loss of consciousness under anesthesia is not simply deep sleep, but a distinct brain state with its own signature. One especially revealing feature of anesthesia is its effect on memory. Under many anesthetic agents, memory formation is disrupted before consciousness is fully lost. Patients may later report that they were awake at some point, but remember nothing. In other cases, consciousness itself disappears before responsiveness does. These dissociations show that awareness, memory, and behavior can be uncoupled in multiple ways. A patient might respond reflexively without awareness. A patient might have awareness without memory. A patient might lose both while brain activity continues. This makes anesthesia a natural stress test for consciousness theories. Any account that equates consciousness with report will struggle to explain cases where patients are conscious but later amnesic. Any account that equates consciousness with behavior will struggle to explain reflexive responses without experience. Anesthesia also reveals how fragile consciousness can be. Small changes in drug concentration can flip experience on or off. Transitions into and out of anesthesia can be abrupt, with little subjective warning. One moment experience is present, the next it is gone. Yet the return of consciousness is often smooth. Patients wake with a sense that no time has passed. From their perspective, the gap simply does not exist. This absence of experience is itself informative. It suggests that consciousness is not something that fades gradually in all cases. Under certain conditions, it can collapse rapidly when network organization crosses a threshold. Importantly, anesthesia is not uniform across the brain. Some regions remain relatively active, others become strongly suppressed. The pattern depends on the drug, the dose, and the individual. This variability has helped researchers identify which aspects of brain organization matter most. Regions involved in integrating information across modalities, maintaining long-range communication, and supporting flexible dynamics appear especially vulnerable. When those systems disengage, experience disappears. At the same time, the brainstem systems that maintain basic physiological function remain active. Breathing, circulation, and basic reflexes continue. Consciousness is not required for life to proceed. This separation reinforces a central theme. Consciousness is not the brain at work. It is a particular mode of brain organization. Anesthesia removes that mode while leaving much else intact. From a scientific standpoint, this is invaluable. It shows that consciousness can be selectively manipulated without destroying the system that supports it. It provides a controlled way to test predictions, rule out alternatives, and refine models. No single theory has yet captured every detail of what anesthesia does to the brain. But all serious theories must now contend with the same core facts. Consciousness disappears when large-scale integration weakens. Consciousness disappears when complexity collapses. Consciousness disappears even when local processing remains. These constraints narrow the field. They do not solve the mystery of why experience exists, but they clarify the conditions under which it does not. Anesthesia, in that sense, is less about sleep and more about silence. Not the silence of inactivity, but the silence of coordination lost. And in that silence, consciousness reveals itself by its absence, offering one of the clearest outlines of what it requires to be present at all. Few areas of consciousness science feel as consequential as the study of disorders of consciousness. Here, questions that are abstract in the laboratory become immediate and human. Is there awareness present or not? Is experience absent, diminished, or simply hidden? And how confident can anyone be in the answers? These conditions force science to confront its limits, because consciousness cannot be directly observed, yet decisions must still be made. The term disorders of consciousness refers to a group of clinical conditions that follow severe brain injury, often caused by trauma, stroke, oxygen deprivation, or infection. What unites them is uncertainty about the presence and degree of conscious experience. The most familiar of these conditions is coma. In coma, patients show no signs of wakefulness or awareness. Their eyes remain closed. They do not follow commands. They do not show purposeful responses to stimuli. Sleep-wake cycles are absent. Brain activity is profoundly altered, and responsiveness is minimal or non-existent. Coma is usually a transient state. Patients may recover, progress to another condition, or deteriorate further. Prolonged coma is rare, and when it persists, it often transitions into other forms of impaired consciousness. One such form is the vegetative state. In the vegetative state, patients regain wakefulness without clear awareness. Their eyes may open and close, sleep-wake cycles return. They may breathe independently and show reflexive behaviors such as grimacing, chewing, or withdrawing from pain. What is missing is evidence of conscious experience. Patients in a vegetative state do not reliably follow commands. They do not show purposeful communication. Their behaviors appear automatic rather than intentional. From the outside, the body looks awake, but the mind seems absent. This condition has also been referred to as unresponsive wakefulness syndrome, a term intended to emphasize behavior rather than assumption. The change in language reflects growing caution about equating outward signs with inner states. Between coma and the vegetative state lies another category, the minimally conscious state. Patients in a minimally conscious state show inconsistent but reproducible signs of awareness. They may follow simple commands on occasion. They may track objects with their eyes. They may show emotional responses that appear contingent on context. The key word here is inconsistent. A patient might respond clearly one day and not the next. awareness flickers. Experience may be present at times and absent at others. This variability makes diagnosis extremely challenging. The distinctions between these states matter deeply. They guide medical care, rehabilitation decisions, and ethical judgments. Yet making those distinctions reliably is far from straightforward. Traditional diagnosis relies heavily on behavioral assessment. Clinicians observe responses to commands, stimuli, and interaction. Standardized scales are used to reduce subjectivity. Even so, misclassification rates have been reported to be significant. A patient may be aware but unable to move, speak, or consistently respond. Motor impairment, fatigue, sensory deficits, and fluctuating arousal can all mask awareness. From the outside, absence of response can look identical to absence of experience. This problem became dramatically clear through the work of Adrian Owen and colleagues. Using functional brain imaging, Owen's team asked patients diagnosed as vegetative to imagine performing specific mental tasks, such as playing tennis or navigating through familiar spaces. In healthy individuals, these tasks reliably activate distinct brain regions. In a subset of patients, the same patterns appeared. Although the patient showed no outward signs of awareness, their brain activity changed in systematic ways when given instructions. In some cases, patients were even able to answer yes or no questions by switching between imagined tasks. These findings revealed the existence of covert awareness. The patients were conscious in some meaningful sense, yet completely unable to express that consciousness through behavior. Their awareness was hidden, not absent. This discovery reshaped the field. It showed that behavioral assessment alone can underestimate consciousness. It demonstrated that brain-based measures can sometimes reveal awareness where none was thought to exist. And it raised profound ethical questions about diagnosis, care, and quality of life. At the same time, the findings demanded caution. Not all patients show covert awareness. The absence of brain responses does not prove absence of experience. Brain imaging is noisy, expensive, and not always feasible. False positives and false negatives remain possible. Interpreting these signals requires care. A brain response indicates task following, not necessarily rich experience. Awareness may be present in degrees that are difficult to classify neatly. These complexities highlight a central challenge. Consciousness is graded, variable, and context-dependent, but clinical categories are discrete. A patient is labelled as vegetative or minimally conscious, even though their inner state may fluctuate along a continuum. This mismatch creates risk. Misclassification can lead to inappropriate care, premature withdrawal of treatment, or missed opportunities for rehabilitation. Overconfidence in either direction can cause harm. For this reason, modern approaches increasingly combine multiple measures. Behavioral assessments are supplemented with brain imaging, electrophysiological recordings, and careful longitudinal observation. No single test is treated as definitive. Instead, converging evidence is sought. These efforts also force theories of consciousness to confront reality. Any theory that equates consciousness with behavior struggles with covert awareness. Any theory that equates consciousness with specific brain signals must explain why those signals appear in some cases and not others. The clinical data do not politely fit into tidy models. They instead impose constraints. Consciousness can exist without overt behavior. Consciousness can fluctuate rapidly. Consciousness can be present in severely damaged brains. At the same time, the data remind us of the limits of inference. Even the most advanced imaging cannot fully reveal what experience, if any, a patient is having. Science can detect patterns associated with awareness, but it cannot enter the first-person perspective. This uncertainty carries ethical weight. Decisions about life support, pain management, communication attempts, and long-term care hinge on judgments about awareness. Families and clinicians must navigate between hope and realism, often with incomplete information. In this context, humility becomes a scientific virtue. The history of disorders of consciousness shows how easily awareness can be underestimated. It also shows how tempting it is to overinterpret new technologies. Responsible progress lies in acknowledging both risks. What this field ultimately demonstrates is something both sobering and instructive. Consciousness is not guaranteed by wakefulness. It is not guaranteed by behavior. It is not guaranteed by any single brain measure. Yet it can persist, quietly and stubbornly, even when the usual signs are gone. Disorders of consciousness therefore stand at the intersection of science, medicine, and ethics. They force theories to confront real lives. They force measurement tools to prove their worth. And they force researchers to admit what is not yet known. In doing so, they reveal something essential, that consciousness is not only a scientific puzzle, it is a human one. Consciousness often feels inseparable from the self. Experience seems to arrive already owned. Thoughts feel like they belong to someone. Sensations feel located in a body that feels like mine. Actions feel initiated by an agent who feels like me. Yet careful study shows that consciousness and selfhood, while closely related, are not the same thing. The sense of self turns out to be something constructed, flexible, and surprisingly fragile, layered on top of experience rather than identical to it. One useful way to approach this is to distinguish between two different aspects of selfhood. The first is often called the minimal self. The minimal self refers to the immediate sense of being a subject of experience. It includes the feeling that experiences are happening here from a particular point of view, and that sensations are happening to this body. It does not require memory, language, or a personal story. It is present in the moment, thin but persistent. The second is the narrative self. The narrative self is the extended sense of identity built from memory, beliefs, personality traits, social roles, and life history. It is the story a person tells about who they are, who they have been, and who they might become. This self unfolds over time rather than existing entirely in the present. These two aspects usually blend seamlessly. Experience feels owned by a stable person with a past and a future, but they can come apart. Dreaming provides one example. During dreams, experience continues vividly, but the narrative self often loosens or disappears. The dreamer may accept impossible situations without question. The minimal self remains, but the broader story of who one is can fragment. Certain neurological and psychiatric conditions show similar dissociations. People can retain consciousness while losing access to autobiographical memory. Others may retain their life story while experiencing disruptions in bodily ownership or agency. These dissociations suggest that selfhood is not a single thing, but a collection of processes layered onto conscious experience. Two of the most important components of the minimal self are agency and ownership. Agency refers to the sense that an action is initiated by oneself. Ownership refers to the sense that a sensation or body part belongs to oneself. These often coincide, but they can also be teased apart. In everyday life, moving an arm feels both intentional and owned, but experiments can disrupt this pairing. One of the most famous demonstrations is the rubber hand illusion. In this experiment, first reported in a modern form by Matthew Botvinnik and Jonathan Cohen, a participant places one hand out of view, while a realistic rubber hand is positioned in front of them. Both the hidden real hand and the visible rubber hand are stroked synchronously. After a short time, many participants report a striking experience. The rubber hand begins to feel like it is part of their body. If the rubber hand is threatened, people may flinch. Skin temperature in the real hand can change. The brain appears to update its model of the body based on correlated sensory signals. This illusion reveals something important. The sense of bodily ownership is not fixed, it is inferred. The brain integrates visual, tactile, and proprioceptive information to decide what counts as the body. When those signals align convincingly, ownership can be reassigned. The experience is not a belief or a trick. Participants often know intellectually that the rubber hand is fake, yet still feel as if it belongs to them. Conscious experience and explicit knowledge diverge. Agency can be manipulated in similar ways. In some experiments, people can be led to feel that they caused an action that was actually generated externally, or to feel that their own action was not fully their own. Timing, expectation, and feedback play crucial roles. When predicted outcomes match observed outcomes, agency is strengthened. When they mismatch, agency weakens. These findings suggest that the sense of self is closely tied to predictive processes. The brain constantly predicts the sensory consequences of actions and compares them to what actually happens. When prediction and outcome align, actions feel self-generated. When they do not, actions can feel alien or externally controlled. Importantly, none of this requires consciousness to disappear. People can be fully conscious while their sense of ownership or agency is altered. Experience continues, but its structure changes. This separation is critical for understanding altered states, including psychedelic experiences, depersonalization, and certain meditative states, where the sense of self may loosen or dissolve while awareness remains vivid. From a theoretical standpoint, these findings reinforce a key point. Consciousness does not require a strong sense of self. Experience can occur without a detailed narrative identity. It can even occur with a disrupted sense of bodily ownership or agency. What changes is not awareness itself, but how that awareness is organized and interpreted. Some theories propose that the self is a model constructed by the brain to organize experience and guide behavior. On this view, the self is useful rather than fundamental. It helps predict outcomes, maintain coherence over time, and coordinate action, but it is not identical to consciousness. This idea aligns with evidence from illusions and dissociations. If the self were the source of consciousness, altering self-representation should extinguish awareness. Instead, awareness persists, sometimes with greater clarity, even as the sense of self shifts. This does not mean the self is an illusion in the sense of being unreal. It is real as a process, but it is not fixed, indivisible, or immune to manipulation. The distinction between minimal and narrative self also helps explain why changes in self-experience can feel so unsettling. Disruptions to the minimal self affect the immediate sense of being located in a body or initiating actions. Disruptions to the narrative self affect identity, continuity, and meaning. Both can be altered independently, and both can change without consciousness itself being lost. From a scientific perspective, this separation allows more precise questions. Which brain processes support awareness itself? Which support bodily ownership? Which support agency? Which support autobiographical identity? Lumping these together under a single label obscures important distinctions. The study of selfhood therefore complements the study of consciousness by showing what awareness is not. It is not identical to identity. It is not identical to ownership. It is not identical to agency. These are constructions layered onto experience, usually so smoothly that they feel inseparable. Illusions like the rubber hand illusion do not diminish the reality of experience. They reveal how that experience is assembled. They show that the brain's model of the self is flexible, negotiable, and responsive to evidence. This flexibility is not a flaw. It is what allows adaptation. But it also means that the sense of self can change under altered conditions, without awareness disappearing. That insight sets the stage for understanding more dramatic alterations of selfhood, where experience remains but the boundaries of self dissolve even further. Consciousness, it turns out, can survive the loss of many things we take to be essential, even the feeling of being a self. Altered states of consciousness offer something that laboratories rarely get on demand. They push experience away from its everyday balance without destroying it. When perception, emotion, selfhood, and meaning all shift at once, theories of consciousness are forced into the open. Whatever claims to explain awareness must still make sense when the usual assumptions break down. Psychedelic states have therefore become valuable stress tests. Before going further, it helps to define one term carefully. A hallucination is an experience that feels real to the person having it, but is not caused by corresponding input from the external environment. That definition matters. Hallucinations are not simply mistakes or imagination. They are genuine experiences, often vivid, structured, and emotionally powerful, generated internally by the brain. Dreams are one familiar example. Certain psychiatric conditions provide others. Psychedelic states add a controlled, temporary version that can be studied systematically. Classic psychedelic compounds such as psilocybin and lysergic acid diethylamide share a common biological feature. They strongly affect signaling at the serotonin 2A receptor, a receptor densely expressed in cortical regions involved in perception, cognition, and integration. Research into this receptor has shown that activating it alters how brain networks communicate. Instead of reinforcing the usual patterns, activity becomes more fluid, less constrained, and more exploratory. Brain regions that normally remain relatively segregated begin to interact more freely. This shift has been described in plain terms as a loosening of the brain's usual organization. Perception under psychedelics often becomes more intense, more detailed, and more unstable. Colors may appear unusually vivid. Patterns may emerge spontaneously. Boundaries between senses can blur, leading to experiences where sounds feel visual or shapes feel emotional. Importantly, these experiences are not random noise. They follow patterns, the same kinds of visual motifs, distortions of time, and changes in self-experience appear repeatedly across individuals and cultures. This consistency suggests that psychedelic states reveal something about how perception is normally constrained, rather than creating something entirely new. From the perspective of predictive processing, psychedelic states are especially informative. If perception is shaped by predictions held by the brain, then altering the precision of those predictions should change experience. Psychedelics appear to do exactly that. Top-down expectations lose some of their stabilizing grip, while bottom-up signals gain influence, even when those signals originate internally. The result is a world that feels less filtered and less controlled. Small fluctuations in neural activity can be amplified into full experiences. Patterns that would normally be suppressed become visible. The brain explores alternative interpretations of reality with less resistance. This aligns well with reports of increased novelty, surprise, and openness during psychedelic states. At the same time, integrative theories of consciousness also face a challenge here. Despite the dramatic changes in experience, consciousness itself does not disappear. In many cases, it becomes richer rather than poorer. This suggests that high levels of integration are not always required for stable, meaningful experience. Instead, integration may shift in form, becoming more flexible and less hierarchical. Studies using brain imaging have shown that under psychedelic compounds, measures of network segregation decrease. Regions that normally form tightly knit communities become more interconnected. The brain explores a wider repertoire of states. Some researchers describe this as an increase in neural entropy, meaning a broader range of activity patterns. This does not imply chaos. It implies diversity. Experience reflects that diversity. Thoughts may branch rapidly. Associations may feel unusually deep. Emotional responses may be amplified or recontextualized. The sense of self may soften or dissolve, sometimes described as ego dissolution. Crucially, these changes occur without loss of wakefulness or basic responsiveness. People remain conscious, often acutely so. The alteration lies in how experience is structured, not in whether experience exists. This makes psychedelic states particularly useful for separating consciousness from selfhood. Many individuals report a reduced sense of being a separate, bounded self, while awareness itself remains clear. Experience continues without the usual narrative anchor. This reinforces the idea that consciousness does not require a strong sense of identity. From a neural correlates perspective, psychedelics also complicate simple models. If consciousness depended on a specific pattern of widespread activation, psychedelic states might be expected to reduce awareness. Instead, awareness often intensifies. If consciousness depended on stable global broadcasting, the increased variability and fluidity might be expected to disrupt experience. Yet experience persists. These observations suggest that consciousness can tolerate, and perhaps even thrive under, a wider range of network configurations than previously assumed. Modern research into these states has been carried out carefully and conservatively by institutions such as the Johns Hopkins Centre for Psychedelic and Consciousness Research and the Imperial College London Centre for Psychedelic Research. These groups emphasize controlled settings, rigorous measurement, and cautious interpretation. Their work has shown that altered states are not merely curiosities. They can produce lasting changes in mood, outlook, and behavior, sometimes persisting long after the acute effects fade. This has renewed interest in their therapeutic potential, while also underscoring the need for careful oversight. For theories of consciousness, the key contribution of psychedelic research is not any single finding, but the pattern they collectively reveal. Experience can be dramatically reorganized without being extinguished. Perception can be internally generated yet feel real. The sense of self can dissolve while awareness remains. Any theory that equates consciousness with normal waking organization struggles here. At the same time, psychedelic states do not imply that anything goes. There are still constraints. The brain does not lose all structure. Certain patterns recur reliably. Certain capacities remain intact. This balance between flexibility and constraint is informative. It suggests that consciousness depends on a range of viable organizations rather than a single optimal one. The brain can support experience in multiple modes, each with its own character. Altered states therefore serve as natural experiments in possibility space. They reveal which aspects of brain function are essential for awareness and which are negotiable. They show how perception, meaning, and selfhood can shift independently. And they remind researchers that normal, waking consciousness is just one stable configuration among many. These states also caution against overly narrow definitions. If consciousness were defined only by clarity, rationality, or control, psychedelic experiences would be dismissed as degraded or distorted. Yet many individuals describe them as among the most meaningful experiences of their lives. Science does not need to endorse those claims to take the data seriously. It needs only to recognize that consciousness can take forms that challenge everyday intuition. In that sense, altered states do not undermine the study of consciousness. They enrich it. They force theories to stretch, adapt, and sometimes retreat. They expose assumptions that hold only under ordinary conditions, and they demonstrate that awareness is not fragile in the way once imagined. Consciousness can bend without breaking, and by observing how it bends, science gains a clearer picture of what holds it together in the first place. As the science of consciousness has matured, one lesson has become increasingly clear. No single theory gets a free pass. Elegant ideas, intuitive metaphors, and impressive explanations all have to face the same test. They must make predictions that can be checked against data, and they must survive contact with results that were not designed to flatter them. This has pushed the field toward a more disciplined phase, one focused less on defending camps and more on structured comparison. Out of that shift came an unusual but increasingly important practice, known as adversarial collaboration. The idea is straightforward in principle, even if difficult in practice. Researchers who support competing theories agree in advance on experimental designs, predictions, and criteria for interpretation. Instead of arguing after results appear, they lock in their expectations beforehand and let the data speak. In fields where theoretical disagreement runs deep, this approach offers a way forward that does not rely on persuasion or rhetoric. Consciousness science is an ideal candidate. Theories such as global workspace accounts, integrated information approaches, recurrent processing models, higher-order theories, and predictive frameworks often explain the same data in different ways. Without carefully designed tests, disagreement can persist indefinitely, with each side emphasizing different aspects of the evidence. Adversarial collaboration forces specificity. A theory must say not just what usually happens, but what should happen in a carefully controlled situation, where alternatives make different predictions. It must risk being wrong. One prominent example of this approach involved researchers aligned with global neuronal workspace models and those aligned with integrated information theory. Both camps agreed to test their predictions using the same experimental paradigms, the same measurements, and the same analytical methods. This did not magically settle the debate. What it did do was narrow it. Certain predictions were supported, others were weakened. Some findings were compatible with both accounts. Importantly, the results exposed which aspects of each theory were doing real explanatory work, and which were more flexible than advertised. This kind of outcome is not a failure. In science, reducing the space of plausible explanations is progress. Adversarial collaborations also help address a long-standing problem in consciousness research: interpretive flexibility. Because consciousness cannot be measured directly, many experiments rely on proxies. Behavior, report, brain activity, and physiological signals all provide partial views. Without agreed standards, the same data can be interpreted in multiple ways. By committing in advance to specific interpretations, adversarial teams reduce the temptation to reinterpret results after the fact. This discipline becomes especially important given the broader replication challenges facing neuroscience. Over the past decades, many fields have confronted the reality that some published findings do not replicate reliably. Small sample sizes, flexible analysis pipelines, and publication bias have all contributed. Consciousness research is not immune. Experiments are often complex and expensive. Patient populations can be rare. Imaging data are high-dimensional. Without care, false positives can creep in. Replication, therefore, plays a crucial role. Independent labs repeating the same experiment using the same methods provide a check on over-interpretation. Large-scale pre-registered studies, where hypotheses and analyses are specified in advance, further strengthen confidence. Measurement challenges remain a central concern. Different methods capture different aspects of brain activity. Electroencephalography offers excellent timing but limited spatial detail. Functional imaging provides spatial resolution but blurs fast dynamics. Perturbation methods add causal leverage but introduce their own complexities. Combining these methods is powerful, but it also multiplies analytical choices. This is where large neuroscience initiatives have begun to matter. Projects supported by organizations such as the Human Brain Project and the Brain Initiative aim to standardize tools, share data, and support collaborations across institutions. Their goal is not to dictate theories, but to improve the reliability and comparability of evidence. By creating shared data sets and common frameworks, these initiatives reduce duplication and allow theories to be tested against richer evidence. They also make it harder for any single narrative to dominate unchecked. Another important development has been the growing emphasis on distinguishing predictions from post hoc explanations. Many theories of consciousness are good at explaining existing findings. Fewer are equally strong at predicting novel outcomes. Adversarial testing pushes theories into that predictive mode. For example, a theory might predict that under certain conditions awareness should persist without report, while another predicts that report-related signals are essential. Designing experiments that isolate those conditions allows the predictions to be evaluated directly. Similarly, theories differ in how they treat local versus global activity, integration versus differentiation, or stability versus variability. Carefully crafted paradigms can make these differences visible. What often emerges is not a clean winner, but a clearer map. Some theories explain certain phenomena well but struggle elsewhere. Others capture broad patterns but lack detail. Some make strong claims that require refinement when faced with data. This process has shifted the tone of the field. Where debates once revolved around which theory was right, they increasingly focus on which aspects of which theories are right under which conditions. Hybrid models are explored, concepts are sharpened, excess claims are trimmed. Importantly, this does not mean that the field is converging on a single unified theory anytime soon. Consciousness is complex enough that multiple explanatory layers may be required. Functional roles, intrinsic structure, local dynamics, self-representation, and predictive inference may all contribute in different ways. Adversarial collaboration does not eliminate disagreement. It makes disagreement productive. It channels energy away from endless argument and toward experiments that everyone agrees would be informative regardless of outcome. There is also a cultural shift underway. Younger researchers are often trained with greater emphasis on openness, pre-registration, data sharing, and methodological transparency. These practices make it easier to compare results across labs and theories. They also make it harder to hide behind vague claims. In this environment, theories that cannot generate clear predictions gradually lose influence, not through confrontation, but through neglect. Theories that adapt, clarify, and survive testing become more precise, even if they never achieve total dominance. This brings the discussion to an important philosophical point. Science does not require final answers to make progress. It requires constraints. Each well-designed experiment that rules out certain possibilities tightens the net. Each replication strengthens confidence. Each failed prediction forces revision. In the study of consciousness, this incremental approach is especially valuable. The subject resists simple measurement. Intuition is unreliable. Language is slippery. Without disciplined methods, it is easy to mistake eloquence for explanation. Adversarial collaboration, replication, and large-scale initiatives help counter those risks. They do not solve the mystery of why experience exists, but they make it increasingly difficult to ignore what the data actually say. This is how a field matures, not by declaring victory, but by learning how to disagree well, by designing experiments that everyone respects, by accepting results that disappoint expectations, by letting evidence narrow possibilities rather than inflate claims. The science of consciousness is now firmly in that phase. Theories are no longer judged solely by their appeal or ambition, but by how they behave under pressure. What emerges is not closure, but structure. A landscape where some paths are closed, others remain open, and a few lead somewhere new. And that in science is exactly where progress lives. After all the experiments, theories, case studies, and debates, it is worth returning to where this exploration began. Consciousness is experience, not intelligence, not behavior, not language or memory or control. Just the fact that something is happening from the inside. That simple definition has quietly guided every serious scientific attempt to understand awareness. And despite deep disagreements, a surprising amount of common ground has emerged. One of the strongest points of convergence across modern theories is this: consciousness is not identical to information processing. The brain can process vast amounts of information without experience ever arising. Blindsight, neglect, unconscious perception, and automatic behavior all demonstrate this clearly. Whatever consciousness is, it is not guaranteed by computation alone. Another area of agreement concerns wakefulness. Being awake is not the same as being conscious. Sleep, dreaming, anesthesia, and disorders of consciousness all show that awareness can fade, fragment, or transform independently of basic arousal. Consciousness depends on specific patterns of brain organization, not merely on the brain being active. There is also broad agreement that consciousness is selective. Experience does not include everything the brain does. It highlights some contents while leaving others in the background, or entirely outside awareness. Attention interacts with this selectivity, but does not fully explain it. Awareness has its own constraints. Across many approaches, another shared insight has emerged. Consciousness appears to depend on relationships, not locations. Early hopes of finding a single center of consciousness have faded. Instead, evidence points toward patterns of interaction, recurrence, integration, and coordination. Whether these patterns are local, global, or layered remains debated. But the focus has shifted decisively away from isolated hotspots. There is also growing agreement on what consciousness is not. It is not equivalent to report. It is not equivalent to confidence. It is not equivalent to frontal activity. Report, confidence, and frontal engagement often accompany awareness, but they can be dissociated from it. Treating them as definitions rather than correlates leads to systematic error. Where theories diverge is in how they interpret these shared constraints. Global workspace accounts emphasize widespread availability. They see consciousness as what happens when information becomes shareable across many systems. Integrated information approaches emphasize intrinsic structure. They identify consciousness with specific patterns of integration and differentiation, regardless of function. Recurrent processing models locate awareness in feedback loops within sensory systems. Higher-order theories tie experience to self-representation. Predictive frameworks focus on inference and expectation. Each captures something real. Each also leaves something unexplained. Global workspace theories explain flexibility, reportability, and task generality well, but struggle with cases of vivid experience without report. Integrated information theory takes phenomenology seriously, but faces challenges of measurement and counterintuitive implications. Recurrent processing accounts align neatly with timing data, but leave open questions about unity and integration. Higher-order theories clarify awareness of experience, but raise questions about whether awareness requires self-reference. Predictive processing unifies perception and cognition, but does not specify what makes a prediction conscious. These disagreements are not failures, they are signals. They indicate that consciousness is not a single problem with a single solution, but a cluster of related problems that may require multiple explanatory layers. Expecting one framework to do all the work may be unrealistic. Another important limit has become clear. Science operates from the outside. Experience is known from the inside. No matter how advanced measurement becomes, this gap will not vanish. Brain data can constrain theories, it can rule out claims, it can reveal patterns, but it cannot directly deliver subjective experience itself. This is not a weakness of neuroscience, it is a structural feature of the problem. The fact that experience is first person, while evidence is third person, means that all scientific accounts of consciousness must rely on inference. The goal is not certainty, but convergence. That convergence has improved. Carefully designed experiments now distinguish processing from awareness more reliably. Clinical cases expose selective breakdowns. Adversarial collaborations force theories to make clear predictions. Large-scale initiatives improve replication and data quality. Progress has been slow, but it has been real. At the same time, important questions remain open. Does consciousness require global integration, or can it arise locally under some conditions? Is there a minimal neural signature of experience, or only families of patterns? How tightly is awareness linked to self-representation? Can consciousness be meaningfully graded, or does it involve qualitative thresholds? These are not idle philosophical puzzles, they guide experimental design and interpretation. There is also a deeper question that science approaches cautiously. Why does any of this feel like anything at all? Here, restraint matters. Some researchers believe this question will eventually be answered by refining existing theories. Others believe it reflects a conceptual boundary rather than a technical gap. Science has not yet settled this, and pretending otherwise would be premature. Importantly, acknowledging this limit does not stall progress. Science routinely works within constraints. Physics does not require an answer to why there is something rather than nothing in order to describe how matter behaves. Biology does not require a final account of life's origin to explain metabolism or evolution. Similarly, consciousness science can advance by mapping conditions, mechanisms, and relationships, even if the deepest metaphysical question remains open. Framing this remaining mystery as a constraint rather than a failure is crucial. It reminds researchers to avoid overclaiming. It encourages precision over poetry. It keeps theories grounded in what can be tested. It also protects the field from drifting into unfalsifiable speculation. There is a quiet discipline at work here. When scientists say that consciousness depends on certain patterns of activity, they're not claiming to have solved experience. They are identifying what must be present for experience to occur, given current evidence. When they say that experience disappears under anesthesia or fragments in neglect, they are not explaining why it disappears. They are documenting when it does. This careful separation between description and explanation is a strength. not a weakness. It allows knowledge to accumulate without pretending to finality. From this perspective, the current state of consciousness science looks less like confusion and more like a structured landscape. Some paths have been closed, some ideas have been constrained, some assumptions have been overturned, others remain open but no longer unconstrained. Perhaps the most important lesson to emerge is a humbling one. Consciousness is not as tightly bound to intelligence, language, or identity as once assumed. It can persist without memory. It can vanish without silence. It can fragment without collapse. It is robust in some ways and fragile in others. That combination makes it scientifically approachable, but not trivial. As the field moves forward, progress is likely to continue in the same spirit. Through careful experiments rather than grand declarations, through comparison rather than allegiance, through accepting partial answers rather than forcing closure. Consciousness may never be reduced to a single equation or mechanism, but it does not need to be. Science can succeed by clarifying what experience depends on, how it varies, and where its boundaries lie. In doing so, it transforms the question from an unspeakable mystery into a disciplined inquiry, one that respects both the intimacy of experience and the limits of explanation. What remains open is not a failure of science. It is an honest reflection of the kind of thing consciousness is. Something deeply familiar, something structurally constrained, something not yet fully explained, and something that, for now, science can approach most productively by knowing exactly how far it can go, and no further. Consciousness turns out to be neither mystical nor simple. It is experience itself, shaped by how the brain is organized, connected, and constrained. Across many approaches, science now agrees on several core points. Awareness is not the same as intelligence or behavior. It is not guaranteed by wakefulness. It depends on patterns of interaction rather than single locations, and it can change, fragment, or disappear in lawful ways. At the same time, no single theory captures everything. Different models illuminate different aspects of experience, and each leaves genuine questions unanswered. That is not a weakness of the field. It reflects the complexity of what is being studied and the limits imposed by the fact that experience is first person while evidence is third person. What science can do, and does well, is map the conditions under which experience appears, alters, and fades. It can rule out false equivalences, test competing predictions, and narrow the range of plausible explanations. What remains open is not a failure to try hard enough, but a boundary that has become clearer with every careful study. Consciousness is no longer beyond science, but it is not yet finished by it either.